Okay, so directly I will start. No need of introduction. Yes, last time Madam has given a nice introduction. So today I will request Madam from
Okay, sir. Okay, sir.
yeah,
Thank you,
that's
sir.
so yes. Okay, so I think clearly I'm audible. Now I will share the screen. So participants, so if at some moment during this session I am suppose I am not audible, then you can directly call to Madam so that I will get to know that I am clearly audible or not. Also, you can type in chat box. That will help us. Just to share my screen. Yes, I hope that now my screen is visible. Madam, can you please confirm?
Is it visible, sir?
Okay, thank you, madam. Yeah, so today, so mainly our discussion topic will be that we will try to implement NSGA2 multi-objective genetic algorithm using Python programming language. So as I told in the last session, that in last session we clearly understood, we clearly discussed that what are the logics behind this NSGA2 non-dominated sorting genetic algorithm 2. So initially, yesterday, I can remember that I told very little bit regarding genetic algorithm. Then I discussed quite clearly in very much elaborated manner regarding this NSGA2. So I hope that now all concepts regarding NSGA2 will know. So assuming that, so we'll start this implementation of NSGA2. Again, participants, please feel free to ask me any questions or to interrupt me during my presentations. Also, you can ask me at the end of the session, whatever you feel better. But since the entire this Python programming, this is totally related with this NSGA2, whatever we have discussed in the last session. So, if you are unable to understand, then please tell me. Once again, I will explain the topic, concept, whatever I explained in the last session. So here I'll assume that all of my participants are a little bit comfortable with this Python programming language. So I'll not go a detailed explanation regarding this Python programming language. Rather than I will focus on this exact implementation part. And whatever will come during the implementation, whatever tools I'll use, whatever logic I'll use, obviously all of the logics I'll try to explain very clearly. So since it is Python programming language, so here I will try to explain using this this Google Colab. This is Google Colab Laboratory. So I hope that all of you are a little bit familiar with this Google Colab. Again, so if I need to say something regarding this Python programming, so what I should say that I hope you know that almost in many, almost what I can say that Python programming we are using almost in many places mainly to solve this optimization techniques. Python programming has very much familiarity. And I can say that Python simply, in the simplest sense, that is, as you know, it's very much popular in language. I can say this is very much interactive. And one of the important concepts behind this Python programming, I should say, that is object oriented. And also at the same time, it is a high level programming language. So once you know the programming, I think all of you know C, C++, or Java programming. So if I ask you to write some code for the same problem using C, C++, Java, and Python, then those who know Python maybe they will feel comfortable because many modules we can directly use in Python, and Python is a little bit easier to understand rather than C, C++, and Java. And what I can say, one more thing regarding Python programming is that today Python has a very high demand. Okay, and basically all the industries or all major companies, they are looking for this Python programmer. So that Python programming is, that's why very much significant in today, in our real life. All of the big companies, big names, they are looking for the, I think, good Python programmers. So once they want to develop some websites, I think maybe software components and simply maybe some applications. And as you know, that Python is very much well related with the data science, AI, and machine learning, which are the emerging technologies today. Yeah, so based on this simple introduction, so I'll not go anymore. Now directly we start we come to our topic. So today, we will try to solve a multi-objective optimization problem using this Python programming language. Multi-objective optimization problem, as you have seen in my last session, that means those may have multiple number of objectives. Okay, the objectives at the same time that may conflict with each other. So here I will show you a very much simple database. So for the sake of simplicity, so I have made the database very much simple. It is not any typical kind of database. Very much simple one. So it will be easier for us to understand. So this is a virtual machine kind of thing. So here see that. So we have considered 10 virtual machines. This VM1, VM2, VM3, VM4, VM5, all up to VM10. So these are my virtual machines, okay? And these are my tasks. Task 1, task 2, task 3, task 4, like that. So we have total number of 30 tasks. See that. 10 virtual machines along with we have 30 tasks. Okay. Now, so what this table represents? This table represents the cost of virtual one for this task 1. That is this. Okay, some amount I have written. Cost of this of performing this virtual machine over this T2. So this. So these are the cost. So as you know that once we are dealing with the cost, so our objective function is the cost. Then always we want to minimize the objective function. That means cost always should be minimized. That should be our objective. We never want to maximize the cost. Okay, so this is one thing. Virtual machine cost to this task. So another table also. So this is again the same thing. Virtual machines are there as well as some tasks are there. But here, instead of that criteria cost, here we will work with this criteria reliability. As you know that once so we are performing some job, some task, always we want to maximize the reliability. See that. So cost and reliability, these two are the conflicting terms. Okay, so if you want to, always we want to increase the reliability as well as we want to reduce the cost. Here it is given this reliability of virtual machine 1 for implementing for this task 1, for this task 2, and this is for task 3, like that, some data set we have generated. So here I want to mention all these data set are synthetic data set. That means it's all, I have only generated this data set. Okay, so to make our programming very simple, so as I am explaining, so here I have taken only 10 virtual machines and this 30 number of tasks. So this is our database. This is our virtual machine, this database, where we are using 10 virtual machines and 30 tasks, and we are representing using cost as well as using the data. We are representing using cost as well as using reliability. Okay. So this was our database concept. So actually now here we will try to find out that if we apply this multi-objective optimization on these virtual machines, by resolving that cost should be minimum, reliability should be maximum, then what should be our solution? So that is our problem of interest here. Now let's see. Now let's proceed. So I think during this presentation now you will get to know. So you see that. So initially, here I have written import pandas at PG, import this numpy as NP, import time, import this copy. I think now maybe all of you are familiar with these pandas. What is very much once we are working with the data set or some database, then this pandas, this module is very much useful. You can say this panda decision simply. I can say this is an open source library. Okay, so that mainly we use so once we are working with some relational or some level data, so that we can do our operations very much easily. Again, so I can say I should say that this pandas that module that library particularly so it provides various kind of data structures and also data structures as well as operations on those data structures. So mainly it will work with the data set once you are using this pandas, this Python library. So second one you have seen that I have used this NumPy. I think all of you know the concept of this NumPy once you are using Python. So actually again this is I can say that NumPy basically that you use for processing the array. So this is an array processing package I can say. Okay, so array processing means again so it provides a very good performance, very high performance for the multi-dimensional array. Okay, so once you are using the concept of objects and doing some operations on those arrays, so there we can use this NumPy. And here I have imported time. So here whatever that we will use using this time, so so that we use using this in terms of seconds. And copy. So here copy means copy for the objects. We will use this copy module. So this for once we will copy from one object to another object, that time we will use copy. So once I am using copy again, I should say one more thing. So here whatever we have used basically that deep copy. We have used the concept here deep copy. So that is little bit different from the simple copy. Okay, so let me open that. So that will be a little bit clear. Just give me 1 minute. So I need to sign in here. I can directly use that. So here, just I can use that from our this Google that also. Anyway, okay, that's required. So here, whatever I'm explaining that copy basically. So once you use that simply assignment, simply equal to that symbol, that means that whatever you do once you use simple assignment for simply equal to. So that means equal operator. That means simply we create a new variable and simply we can share the reference of that variable. We can say to that original object. But here one should use deep copy. Deep copy means entirely we are copying. So deep copy means here we can say that we will create a new object. We will create a new object, and what about the features of the first object that will be entirely copied to that new object. That means if you do some changes in the new object, so there will be no issue. Okay, it will be working exactly. So that original content of the original object, it will not be changed. So that is the meaning of deep copy. Here I am going to use this deep copy function. So again I am telling, so here deep copy means here I will create, once I will call deep copy, so that will create a new object. And what it will do, so it will copy the content of the original object into the new object. Now if I do some changes in my second object where I have copied it, so my content of the original object will be intact. It will not be in effect. There will be no changes. So that is the purpose I am using this deep copy using this to explain this NSGA2. Okay, so next. So here what I am doing. So since the program I am explaining from this Google Drive, so that means I need to get the access from the Google Drive. So here see that what I am doing. So that means it will give the access. That means I need to mount my Google Drive so that I can access this file from my Google Drive. So that is important here to write this comment that from Google Colab, you need to import this drive and drive.mount. So that is successful. That means I have mounted the content from my Google Drive. Okay, so next you see what I am going to do. Next here I am writing this task VMS cost. So PD, as you have seen, PD means what? PD means pandas. See this pandas library we have written as an object as PD. So PD dot read Excel. So ultimately we have given, I have mentioned here some part. So what does this part mean? So this part means this is the part where I have saved this data set in my Google Drive. Okay. So next I have written sheet name equal to cost. Okay, I have started with this index column 0. See that. In the second case, what I have written, task GMS reliability PD, that means this pandas dot read Excel. So here I have again some part I have mentioned. Then I have written sheet name reliability. So if you look closely to my data set, you will get to know two sheets are there. One is the cost, second one is the reliability. Once again, let's see. See, so this is my cost data set regarding cost. And secondly, this is the data set regarding my reliability. So cost and reliability are these two data sets. So the same thing here I am using like that. So sheet name equal to cost, it will take the data set from cost. And once I am writing sheet name equal to reliability, so it will take the data set from this reliability sheet. So now where I am getting the path. So if I click here, so here you will get to know. So if I click here, so here we will get drive. Okay, so inside the drive, you need to click on my drive. Okay, so inside now by my drive, here actually now, yeah. So the content will come. So all these content are saved in my drive. So here actually I have saved that data set. Okay, so the data set here somewhere it is saved. Now let me check where it is saved. There's so many huge data are there. So let me check. So somewhere it is saved. TMS like that anyway. So anyway, so once we click on that, suppose once we click on some data set, then what will happen? So this let us see TMS if I get, otherwise okay. Yes, I'm clicking on here. Let us see. Okay. Then if I click here copy path, so I can copy the path by this manner. Okay, what about the paths I will copy? So the same path I will paste here. So that is the logic behind that. Okay. So that means this path I have pasted here. That means now I have mounted my drive and I can access the data set from the Google Drive. Okay, to my this now Python programming environment. See here. So task VMS cost. So let me check that it is successfully coming or not. See here. If I click on task VMS cost, you will get to know this data set exactly is there in my Google Drive. Okay, so these are the virtual machines 1 to 10, and these are my tasks. task 1 to 30. That means I have successfully mounted my Google Drive as well as I have successfully copied, okay, that data set into this task VMS cost variable. Okay, next. Next, let's see. So I have copied that data set also, task VMS reliability. Let me click here. Successfully copied or not? Yes. If I click here, you will see successfully I have copied the data set from the Google Drive into my this variable task VMS reliability. I hope up to this point you are getting. So simply I have imported pandas, NumPy, and I have mounted my Google Drive. Why? Because I want to access this on my Google Drive. The data set here I have here this part. This is the part of my data set. Whatever I have stored in the Google Drive. And secondly, again, this is the part of my second data set. And as you have seen, sheet name, cost, sheet name, reliability, that is exactly the name of the data set, whatever I have stored in the Google Drive. That means successfully I have mounted my drive as well as successfully I have imported the data set to my Python programming environment. Up to this point, it is clear. Now let's. So this is my initialization settings. See here. Here, how many tasks are there? So see. So number of tasks equal to 30. So as you have seen, number of tasks equal to 30. See here, this task 1 to task 30. So number of tasks are here 30. What is number of virtual machine? As you have seen, I have considered this number of virtual machine be 10. So 10 number of virtual machines and 30 tasks I have considered to implement my MSCA 2. Okay. Then population size 50. So in the last session, once I was explaining, so I clearly told you population. Population means what? It is a population of some set of chromosomes. Chromosomes means what? Chromosomes means we can say the candidate solution. Each and every solution is termed said as a chromosome. So population size equal to 50. That means my 50 number of chromosomes should be there in each and every population. 50 number of chromosomes will be there from the initial generation, then from the first generation, then to the second generation, like that. Number of iterations here I have considered it is 500. Crossover rate 0.8. As I told you, you can remember crossover rate, mutation rate. How many crossover I will implement? How many mutation I will implement? Okay, that is known as crossover probability and mutation probability. The same thing. Here I have written as crossover rate and mutation rate 0.8. That means 80% simply, and this is the 20% mutation rate. That means if my number of chromosomes are suppose number of chromosomes are 30, that means 24 number of crossovers will be there and 6 number of mutations will be there. So you can remember that I told in the last session that crossover rate is always higher than our mutation rate, and also I explained the logic behind that. That once you implement the crossover, what may happen? Once you implement the mutation, actually, what may happen in the search space? Now, this is our mutation selection rate. Another parameters I have considered, it is 0.4. So once we, I'll explain the fact, then once again I'll explain these parameters in detail. Now, see, this is number mutation job. So here, whatever I have done, round number task into number of mutation selection rate. Now let us see. Okay, let us proceed. So what I have implemented here, I need to run it. So this is the initial parameter settings. Okay. Next, we gradually will move to the computation. Now let's. Here, whatever I have done. So this is simply for the purpose of my coding. I have written that. So task VMS cost equal to this list. See here. Here I have used the concept of list. List map flow, this task VMS cost, I is location, I, for I is range number of tasks. That means what will happen? So whatever the task I have, whatever the things I have considered in my task VMS cost, that particular data set, so everything will come as a list here. Everything will convert as a list here. Actually, so that I have done purely for my experimentation, purely for my programming purpose. No other meaning for that. Now, if you are not not familiar with list, then here I can show you something regarding list also. Now let me check. just 1 minute. So I think, yeah. So again, I have written something for you, that so that the things will be very much clear. Actually, I have copied everything here so that I can save my time better. I can focus more on the explanations. If I start writing, it may take more time for that. See, this is the concept of list. Now, simply what I can use, what I can tell for list. Simply lists are used to store multiple items in a single page. This is little bit different from the concept of array. Okay, so multiple items. So items may be integer type, items may be string type, character type, float type. So every type kinds of items you can store in a list. It's not like that. List will be always of some similar user-defined data types. Similar data types. It's not like that. See, so here what I have given list apple, banana, cherry, list 1, list 2, list 3. These I have given, and this is, and if I execute it, so that means, so this will be my list 1, this will be my list 2. So as a result, I will get it. So this is simply list. So as I told, that we can merge, that we can store various kind of data items in a single variable once you are using list. Here is the example for that. Take it here. So here I have used inside this list ABC. This is string, 34 integer, 2 boolean variables, 40 integer, male. This is also a string. So same thing. So once I execute it, obviously this will be the output. So I hope now it is very much clear that this is the list, concept of list. Now, so once we are using the concept of the list, so simply once again I should tell you very fast that this is the concept of an array. Whatever we can use in Python programming language. Take it here. Import NumPy as NP. So NumPy, as I told earlier, the purpose of NumPy, whatever you are using, this array, np.array. So this is a two-dimensional array. Take how to define it. So once we will print the content of array, that means array is of type. So this will be the array type. This will give array dot this. This will give the number of elements in that array, number of dimensions of the array. This is the shape of the array, and ultimately this will give array dot size. That means this will give the size of that array. Okay, so that means if I run it, whatever you will get. So we will get this out. Okay. Number of dimensions 2, since it is a 2D array. So shape of the array 2 by 3, take it, 2 rows and 3 columns, and number of elements are 6. So simply this is the concept of the array. Okay. So now let me move forward with our original programming. Yeah. Yes. So now you are getting a little bit idea regarding the list. So whatever I have done. So for this is the syntax for the for loop. For I equal to 1 in range number of tasks. So number of tasks means what? So it will up to how much it will proceed. So now just 1 minute. Yes. See, so we have 30 number of tasks here. We have 30 number of tasks. So that means I equal to, so 0 to 29. So for I always start from 0, so 0 to 29. So that is the 30 number of tasks. So that means, so what are the content I have saved in my VMS cost data set. So that will be now listed as a list here. That will be simply stored as a list. And similarly, whatever the things I have used, we have 3 here. So again, task VM reliability. So this is the list. So simply I am converting the data set into list. So this is the for loop. I equal to now for I in range number of tasks. Okay, so now let me check. So whatever I tried to do, that is exactly coming on. Take it here. If I click, if I write it here, then let me check what is the output. Take it here. So simply this is coming in terms of list. Why this is required? Now, as per my programming language, so I have used this to implement the logic in comfortable manner. Okay, so this is converted into list. So now let me check my next thing, tasks VMS reliability. So that is correctly coming or not? Yes, it is also correctly coming. Actually, what was the exact data set? Simply those data set I have converted into list. Okay. Now let me see. See, start time. So start time equal to time, as I am telling that I am using the time library. So like here, whatever the time I will take, so it will be in terms of second only. Okay, now let us come to our main part. Okay, main part of this program. So I'll explain this non-dominated sorting letter. Firstly, I'll come to the initial module. Otherwise, it will be difficult for you to understand. Obviously, I'll explain each and everything. Yes. So this is our main module. Check. So this is our main module. So far what we have done, simply we have set the parameters, okay, and also we have converted the entire data set into list. See, whatever here I am doing. So base list, based object. So that means I am creating some empty array for this base list and based object. Because during my process, during my once I'll proceed with my program, I'll create, I'll get to know, I'll compute this base list and based object. So initially I have creating the empty array for the base list and based object, so that immediately whatever I will get, that I can put in the empty array. Also the population list. Here once I am writing this syntax, that means I am creating an empty array for that. Or simply I can say empty list for that. Now most importantly, whatever I am writing, take it very clear. So for I in range population size. So what is my population size? Yes, my population size is 50. That means I can consider 50 number of chromosomes here in my population. Next, what I am writing? Try to get it. So this random number I am writing list np.random.permutation number of tasks. That means what I am doing here. So here I am trying to generate this 30 number of random numbers. Okay. So this, and then what I am trying to do? So I am trying to 30 random numbers I am generating, and once I am generating the random number, so that means so I am storing in this variable. Okay, random number. Okay. Next, next what I am doing? Let us check next what I am doing. So what I am doing here? So I am trying to create my population here. Okay. So population list, once I am writing population list dot append this random numbers. That means whatever random numbers 30 I have generated, so simply that I am trying to include in my population list. Now you can ask me, sir, why you are generating these 30 random numbers? Okay, so these 30 random numbers only I am generating. Now let me proceed in that manner. I will tell you. See here. So then what I am doing? So for j in range number of tasks. What is number of tasks? See, so number of tasks equal to that 30. Okay, then population list I, take it very clearly, 2D array. Population list ij, that we are finding the remainder of this number of variables. So what does it mean? Number of virtual machines. Number of virtual machines, how many I have considered? The number of virtual machines I have considered 10. You can remember, 10 virtual machines I have considered, as well as with each and every virtual machine, I have considered 30 number of tasks. Now see here. So why I am writing this? Because so once I am generating some random numbers, so the random numbers maybe this is outside of my virtual machine, because I have considered only 10 virtual machines. I have considered only 10 virtual machines. So to make it normalized, so simply I am writing this statement. Okay, now let me proceed. So next what I am trying to do. So simply here I have generated this 30 random numbers, and I have stored in the population list. Okay, 30 random numbers and simply storing in the population list. So that I have done up to this point. Next, whatever I am doing, let's see. For 8 in range number of iteration, what I am trying to do. Yes. So here after generating the initial population, so what I am trying to do. So after generating the initial population, here for the sake of simplicity, I am not implementing any natural selection. So simply I have removed here, I have simply removed the natural selection part here for making the program a bit simple. So directly I will come to the crossover. But I hope that once here I have explained that, so as I told that our population size is what? Population size is 50. See that. So population size is 50. Now what is our chromosome size? Our chromosome size is 30. See. Our chromosome size is 30 because each and virtual machine will be a chromosome. So that means what is the size of the chromosome? You know, each and every virtual machine consisting of 30 number of tasks. See here, once again I will show you. See, each and every virtual machine consists of 30 number of tasks. So that will be the chromosome size here. So chromosome size will be 30. 30 number of genes will be there in each and every chromosome. And genes are nothing but this task. Okay. So how I'm ensuring it in my program? So in my program, how I'm ensuring it that 50 number of populations are there, 50 number of chromosomes are there, as well as each and every chromosome, this size is 30. See here. So in this for loop, if you look closely, whatever I have done, for I in range population size, as you know, what is the population size? So population size is 50. That means, so how many chromosomes we are creating? Check it. So from I carry to 0, here I am creating a chromosome of size 30. Take it. Random number, this random number. How many random number you are generating? 30 random number you are generating. Okay, so each random number belongs to each gene. 30 random number you are generating. So if you combine this 30 random number, what it will give to you? It will give you the chromosome. See here. So that means initially one chromosome you have generated here. Take it very clear. One chromosome you have generated. And that chromosome you have appended to the population list here. See very carefully. Once I have written population list dot append this random number. That means whatever 30 random number I have generated, simply those I have appended to the population list. Is it clear now? That means, so this for loop I am moving from here to 50. That means I am generating 50 chromosomes where each and every chromosome size is 30. Try to get it very clear. How I am generating a population size of 50, where each and every chromosome belongs to, I think, 30 genes. Chromosome size is 30. I hope now this part is clear. 50 chromosomes we have generated, and where the size of each and every chromosome is 30. So from here only I am trying to ensure it. So generating 30 random numbers, okay, and appending it to population list. Now this thing, how many times I'm performing these operations? These operations I'm performing 50 times for I equal to up to 50. Value of I is 50. That means 50 times I am executing these statements. That means I am generating 50 chromosomes. Okay. So now, as I told that to make the program simple, so here I will not use any, natural selection part. Okay. Let us proceed directly to the crossover. Let us take it very clearly, whatever I am writing here. For n in range number of iterations. What is number of iterations? So I have considered 500 iterations here. Next, crossover. So as you can remember, the concept of crossover that was associated with very much simple, I think, genetic algorithm. So you can remember, so what was the concept of crossover there? Crossover means what? Similar to the matching process, and only in technical terms, only exchange of information will be there. If you want to be more technically, exchange of genes will be there. Not the genes, exchange of gene values you can say. So that will be the crossover. And what we have considered that if we consider a couple of chromosomes, a pair of chromosomes, as a result, we will get a pair of offsprings. So that was our discussion topic in the last session. So the same thing here we will implement, try to get it. Here we will try to implement the same thing. I'm not coming to any other different thing. Exactly whatever you have told, exactly same thing we will try to explain here. See whatever I'm doing. Yes. Yeah. So parent list, copy, deep copy. See here. As I told you earlier, what is the meaning of deep copy? So here I am using this module, deep copy. Parent list, copied or deep copy, population list. Now you can ask me, sir, where you are getting the population list? Where I am getting the population list? See here, what is my population list? This is my population list. Initially, I have generated my population list. Yeah. So that means in the population list, how many chromosomes are there? 50 chromosomes are there. What is the size of each chromosome? Size of each chromosome is 30. So that is my population list. So that population list, I'm copying to parent list. So why I have used this copy here? Because my parent list and population list will be entirely different. If I do some changes in the parent list, population list will not be affected. Only that purpose I have done. Okay. So next, offspring list equal to null. That means I am creating a list, null list, empty list for my offspring, whatever I will create. Next we see whatever I have done. Yes, whatever I have done here, let us see here. See. Yes, equal to list np dot random permutation population size. See here. What is my population size? My population size is 50. So that means, so simply I am generating a random sequence. Okay. So to select the parent chromosome to crossover. See here. So simply, as I told that whatever the chromosomes we use for the crossover, those chromosomes will be generated random. We have no biasness. We have no control on the pair of chromosomes. But what is our assumptions? Since we will implement the crossover immediate after the natural selection, so obviously we will have more, I think, more copies of the better string, better solution, and less copies of the poor quality solution. And once we have more number of copies of the better quality solutions, and if we do that crossover, chances is very much higher that again in turn, okay, by applying the crossover on higher quality solutions, we can expect much more better quality offsprings. So that was our hope, that was our expectation once we are implementing the crossover. So similarly, here I have generated a random sequence to select the parent chromosomes for the crossover. Okay, I've generated the list. Okay, so the 50. Now let's see whatever I am doing. Take it very clearly. For M in range, population size by 2. Whatever I have done. So here I am considering, for the sake of simplicity, that all 50 chromosomes are taking part or participating in the mating process. So that is my assumption here. Make the process simple. But actually it is 0.8 probability. But to make it simple, I have written it in different manner. Okay. So once I am writing M in range, population size by 2, that means what? Population size by 2 means 25. Since we have 50 chromosomes, that means now we have 25 pair of chromosomes. See what I am doing here. Parent 1, see here, parent 1, population list 2 into M, this colon. What does it mean? So initially, value of M, it will start from 0. So what will be my population list? So that means, so initially it will be 0, S 0. What is S? S means this list. See, S means this list, which I have randomly generated. I had a population size, 50. From that population size, 50, I have randomly generated some list. Okay, then that list I am dividing in two parts, 25, 25. Try to get it. That thing I am equally dividing in two parts, 25 and 25. Whatever I am doing, so that means 0. So here it will be 0. Okay, so 2 into 0, 0. And next, what will happen? Parent 2. 2 into 0 plus 1. So once M equal to 0. So parent 1, it will come from population list 0. And parent 2, it will come from population list 1. Try to get it. That means 0 and 1. That means now first two chromosomes. Okay. So now first two chromosomes will be parent 1 and parent 2. Take it. So before performing these crossover operations, I have done some randomized operations on the set of chromosomes. So that as we have said, that the pair of chromosomes will be selected randomly. So that means, so here my first chromosome, my second chromosome. What does it mean? So once I am writing this colon, that means entire thing on my first chromosome will be copied to parent 1. Entire thing from my second chromosome will be copied to my parent. So that was the meaning of this colon operator. Normally, we are using once we are doing this list operations, list manipulation operations. Okay, next see. This is my child one. This is my child two. What I am doing? Try to take it very clearly. I am writing child one equal to parent one, child two equal to parent. See, whatever I am trying to do here. Take it very clearly. Whatever I am trying to do here. Simply I am writing child one equal to parent one. This colon, that means whatever the values or contents are there in the parent one, that will be copied into child one. Okay, the content of parent 2, simply that will be copied into child 2. So let us successfully execute it, then I will show you what is happening here. You see that. So in this parent one, 30 items are there. Take it very clearly. Why 30 items? Because this is one chromosome now. Size of chromosome is 30. That's why 30 items here. Simply parent 2, 30 items. Parent 1 is coming from my first population list. See. Parent 2 different, coming from the second population list. Take it here. Child 1 exactly similar to my parent 1, child 2, parent 2. Now let us see what I am doing here. Cut point. Here, as you know, the concept of crossover, that means we need to determine that crossover point random. You know, crossover point you need to determine. And exactly the crossover point will be determined random. So as you can remember, so once we have implemented, once I have shown you only one point crossover. So in that one point crossover, whatever I have shown, then in the one point crossover, we randomly determine the point and we exchange the information beyond that point. Okay. Similarly, here, instead of generating a single point, we are generating 2 points. Okay. So, and what is our assumption? So, if you can remember that what I told in crossover in my last session, we generated only one crossover site or crossover point, exchange the information beyond the crossover point. Here, what we will do? We generate 2 crossover points, not one crossover point. Okay, first chromosome one crossover point, second chromosome second crossover point. Then what will we do? Then we will exchange the information between 2 crossover points on. Try to get it. So I need to generate 2 crossover points. Let us see. Start point. I need to NP random choice number of tasks. Number of tasks. Then we have 30. Then 2. Replace horse. That means here no repetition will be there. So here from this number of tasks, what I am generating? So I am generating 2 random numbers. See, number of tasks is 30. So that means, so out of 30, I am generating 2 random numbers. Wherever the random numbers will not be repeated. That's why I have written replace equal to false. Then what am I writing? Cut point equal to sort. So I have stored the result in the cut point. And cut point equal to sort means what? So whatever the 2 random numbers I am generating, I am sorting it. Okay, so that was my main purpose. Now let's see. Whatever the cut points are generated here, 2 cut points are generated, that is 9 and 15. Obviously, this should be within 30 or cut point dot sort. That means it will come 9 and 15. Sorting. Next, most importantly, try to get it very clearly, whatever I am doing. Child 1, cut point 0 to cut point 1. That means 9 to 15. Cut point 0, what? Cut point 0 is what? Cut point 0, I think it was 9. Yes. And cut point 1, it was 15. So 9 to 15 inside child 1. 9 to 15 equal to parent 2. Cut point 0, cut point 1. So what I am doing, as I told you. Simply from parent 1 and parent 2, you are exchanging only those informations where those informations are in between 9 and 9 is my first crossover point, 15 is my second crossover point. Whatever the content will come between 9 and 15, all those contents simply I am interchanging. So this is this kind of crossover I am using, that is called 2-point crossover. Here I am using the concept of two-point crossover while I am implementing the crossover. I hope now this point, up to this point, is very clear. So here how we have implemented the crossover that I was trying to show. So this is the logic for that. See that cut point 0 to 1 equal to parent 2, cut point 0 to 1. Inside child 2, cut point 0 to 1, that will take from parent 1. This part will take from parent 2 into child 1, and this part will copy from parent 1 into child 2. So we have created two offsprings. Okay. So two parents, we have now created two offsprings. How many times we perform this operations? M times. M means what? What is the value of M? So we are taking randomly. Value of M will be this 25. So offspring dot list dot offspring list dot extend child 1, child 2. That means initially I had with me the list of parents. Now from the list of parents, by implementing the crossover, I am getting the list of offsprings. Offspring list dot extend. That means each and every time I am running this. So the list will be updated. The list will be extended by adding the new values, whatever coming after implementing the crossover. So that is the significance of this statement. Offspring list dot extend child 1, child 2. So now I have successfully implemented the crossover. Okay, so here for the sake of simplicity, I have made the logic very much simple. Now, after implementing the crossover, I will go for mutation. As you have seen that you can remember mutation what we did. We randomly selected some chromosome and ultimately we are changing the values of either one gene, two genes or randomly selected gene. So that was the mutation, and obviously we are implementing the mutation after implementing the crossover. Let us see how we are implementing mutation using this Python program. See here what I am writing. So for every range offspring list, what is the offspring list? What is the length of the offspring list? Obviously, length of the offspring list will be 50. So that means from n equal to 0 to 49. So up to 50. This mutation probability here. Here I have using the concept of mutation probability. NP dot random rank, that will generate a random number that I am assigning to this variable mutation probability. Then whatever I am doing. Okay. So if mutation rate is less than mutation probability. So if you remember, so initially once I did the initial parameters, I explained it, mutation rate, that I considered as I think 0.2 was our mutation rate. So if mutation rate is less than this mutation probability, then what we will do? See here. Here very clear, very carefully, whatever I am trying to do here. List np dot random choice dot choice, what I am doing, check it. Number of tasks, number of mutation jobs, here I am using. Number of mutation jobs is 12. Take it very clearly. Why I am doing it? Now I will explain. Number of mutation jobs initially I had used. You can see. Number mutation jobs. Here, number of tasks 30 into mutation selection rate, that is 0.4. It is becoming 12. So now I am going to explain it. Take it very clearly. Number of tasks, this is 30. Number of mutation jobs, this is 12. Replace equal to false. Once you write replace equal to true, that may take some repeated values. But once you write replace equal to false, values will not be repeated. So that is the significance. So replace is a Boolean variable. Now, what I am doing, check it. np.random.choice from number of tasks. Okay, so from 30 number of tasks. What is 30 number of tasks? 30 genes only. Okay, from 30 genes. So among these 30 genes, randomly I am selecting 12 genes. Take it very clear. Each and every chromosome belongs to 30 genes. That is the chromosome size. So out of the 30 genes, randomly I am selecting 12 genes. Take it very clearly. So all those 12 gene positions, I will try to change the values of that gene. That means here single point mutation I am not using. So here I am using mutation at multiple points. So this will give you the list. See here, 12 items. So it is getting 12 positions. So it is giving you those 12 positions. Okay, in ascending order, not in ascending order, repeated values. So those 12 positions it will give you. So on those 12 positions, gene positions, I will change the gene tag. So that is the significance of this statement. Okay, so this is basically chooses the positions or mutations randomly. Next, see here what I am doing. Here very importantly, here very important thing I am doing. So 12 values I have selected, 12 positions I am selected. What I am doing here. So first listen to me. What I am doing. So just check it. What I am doing here. So T value last. See what I am doing. Offspring list M. Okay, this M, this position is 0. See that. Save the value which is on the first mutation position. So this is our first position. Whatever we selected from here. So this is our first position. So in the first position, so simply I am saving in that time. Why I am doing? Because see, first position simply I am exchanging with the last position. Okay, value of first and last. Now they are getting exchanged. Let us see. Let us proceed. Then you will get to know it. What I am doing. For I equal to ranges, number of mutation jobs. How many jobs are there? 12. Why I am writing number of mutation jobs minus 1? Because 1 I have already considered 1 value here. Out of 12, 1 I have considered, remaining is 11. So that's why I am writing number mutation jobs minus 1. Okay, next what I am doing. So offspring list, this M, this positions, offspring list achievement. So this position I now is replaced with the position I plus 1. Take it very clearly. So position 1 replacing by position 2. Value of position 2 replaced by position 3. Value of position 3 getting replaced by position 4. Value of position 4 replaced by position 5. Similarly, the value of position 1 replaced by last. See, this is a circular manner. This is kind of circular mutation here I am using. See, this is the different kind of mutation technique here we are implementing. As I told, that mutation technique may differ from problem to problem. Whatever I explained, that was using in terms of binary. I think I encoded the chromosome in binary format. That's why all this mutation was explained in terms of this binary format. But as I said, the crossover may be many kind of crossover may be possible. Simply many kind of mutations also may be possible, and those are entirely problem dependent. See here. So I hope now you are getting. So what I am doing? Randomly I have selected 12 positions. Random. Okay. 12 genes, better to say. 12 genes I have randomly selected. And what I am doing? So I am changing the values of those 12 genes. How I am changing the values of those 12? Here I am considering that randomly selected gene value 1 will be copied by gene value 2. 2 will be copied to 1. 3 will be copied to 2. 4 will be copied to 3. Like that, this circular kind of mutation here I am. Okay. Ultimately, what was the purpose? Purpose of mutation was that to change the value of that gene. Randomly, we will select the genes and we will change that. So here, that kind of purpose I have resolved it using this step. So take it out. See here. So once I am doing see offspring list. So what will happen here? So only those 12 I have exchanged. Remaining things are okay only. On the remaining offsprings I have not done it. Only on those 12 selected genes, I have done the necessary changes. The remaining things are exactly okay. So ultimately, after that mutation part, what will be your offspring? Offspring list, obviously, exactly. Number of offspring will be 50 only. It will be 50 only. So what does mean the last statement? Here, what I am doing. So random mutation jobs minus 1, 11, p value last. P value last means what? The value of past. Okay, that means offspring randomly selected past value. So that is now denoted by p value last. So now we are copying that value to this our dual position value. Like that, here we are circularly in circular fashion we are implementing the mutation here. Okay, now let us see. So crossover and mutation is over. So after crossover, what is our population size? Obviously, it is 50. After mutation, what is our population size? Obviously, it is 50 only. Now let us next what I know. Next, I am trying to compute the fitness values. Fitness values of my chromosomes. How to compute the fitness value? Here, what about functions I have used? Let us see what I am doing. Total chromosome, copy the deep copy parent list, copy the deep copy of spring list. What is the need of this step? Now, if you remember that NSJ2, so I told you in NSJ2, so initially after once, okay, so why I am doing it, let me once again show you. Then the things will be a little bit clear. That let me once again open my PPT. So then the things will be a little bit much more clear to you. Why I am making it 2n? Let us show you why I am making it 2. Yes, take it very clearly here. So that means from parent we are getting the offspring, okay, by implementing the crossover mutation natural selection, whatever it may be, from P0 to Q0. Then whatever I am doing in R0, simply I am taking the collection of both P0 plus Q0, parents as well as offspring. Exactly the same thing I am doing there. Try to get it. Exactly the same thing I am doing here. I'm collection, I'm doing a combination or simply I'm taking the summation of this parents chromosome as well as the offspring chromosome. So that means I am getting now 2n chromosomes. So in my case, I am getting now 100 chromosomes. Yes. So that is the total chromosome. I hope now you can map it. So from n to n, that was 2n. So here, my parent list what? It was 50. My offspring list, what is it? It is again 50. So this 50 plus 50, total 2n. N plus n, 2n. That means 100. So total 100 number of chromosomes now I am storing inside this total chromosome. Okay, let us see. Next, chromosome object record. So here I have used, so for some variables, empty variables I have created, empty array I have created. Let us see. For m in range, population size into 2 minus 1. Take it very clear what I am doing here. Population size means obviously 50 into 2 means 100. So that is 0 to 99. So here, what I am writing. So this is the cost and this is the reliability. This variable is related to cost. This variable is related to reliability. See what I am trying to bring here. Let's see. So this is another variable I am creating in range number of tasks. Number of tasks, what is your number of tasks? Number of tasks is 30. See, this is one of my fitness functions. So once I am using the cost, simply I am getting the addition of the cost. See, generation, this is the value of cost plus equal to task virtual machine cost total chromosome this. I hope not you get it. So this is so that task, what is the value of an n? So that means it will move from 0, it will move from this 0 to 29. And what is that? So this value total chromosome m, and ultimately this will move from 0 to 99, and this is the end. That means so total chromosomes we got, and you have seen 100. Okay, so now for each of the chromosomes, so we are trying to find out the cost. Now, how to get the cost? As I was telling, once you are finding the cost, simply you are adding the cost values for each and every chromosome, for each and every virtual machine. See, here the cost of virtual machine 1 would be, if you add the summation of all these costs, that means task 1, task 2, plus task 3, plus task 4, plus task 5, plus task 6, like that. So it will give you the cost of virtual machine 1. Similarly for all other virtual machines. Now, whatever we are doing for reliability, so that is the fitness function we are using for this genetic algorithm for finding the fitness value. So see, so for the reliability, here simply I am multiplying. So for the sake of simplicity, again I am doing it. So here I am multiplying. So I am doing two different kind of operations. Reliability. So I am multiplying the reliability once it is in terms of reliability, and I am multiplying the items or multiplying the values once it is in terms of cost. Okay. So see that. So from this list, as we have seen earlier, I have converted this into list. So from this list, what it will do? It will calculate. Okay, it will compute the values of fitness values of each and every chromosome, and it will save in this variable. Similarly here, from the reliability, it will compute the fitness value of each and every chromosome, and ultimately it will save. It will store in this variable. See here, whatever I am doing. Chromosome, this object record these two things. That means here it will be a couple of values. See how I am getting this 99 or 99 items. How I am getting? Make it very clear. So each and every item, once again check. So item 0 consists of two values. Item 1 consists of two values. Why two values? So first value belongs to reliability. Second value belongs to cost. See. First value belongs to reliability and second value belongs to cost. I hope now it is clear. So in this chromosome object record, this is the objective function. That's why I have written it as an object. So here what I am doing, so I am simply storing the reliability as well as cost of each and every chromosome. Okay, so up to this part it is clear now. So how I am computing the fitness function. Okay, now gradually we will move to that. Whatever I was explaining it with the part of genetic algorithm, now it will come non-deterministic sorting. See here. So up to this part we have done. Okay. Next it will come to the part of environmental selection. So as you know that we need to implement environmental selection to convert or to select the best n solutions from those number of solutions. Here in our example, to select 50 chromosomes out of 100 chromosomes. To select best 50 chromosomes out of those 100 chromosomes. So we will use first non-dominated sorting for the convergence purpose, as well as we use crowding distance sorting for this diversity purpose. Now let us. Okay, so now we move to environmental selection. That means we need to implement this non-dominated sorting. Try to take it very clear. This is the most difficult part here. So from non-dominated sorting, see here what I am passing inside these parameters, inside this module. So population size, chromosome object record. That means population as well as the objective function value for each and every chromosomes we are passing to the non-dominated sorting function. Okay, chromosomes as well as the entire population as well as the objective function values of each and every chromosome we are passing through it. Now let us see non-dominated sorting. Yes, so this is our non-dominated sorting function. See, population size as we have seen earlier. Okay, and this is our chromosome that we have passed it. Now see. So here this is S. N. S be a set list, basically list of those solutions, and N be the counting non-domination count here. So initially we are declaring as empty. Front, rank, those are also empty. So this is the way to define. Next, front 0, that is also empty. So empty list we are creating. Okay. Next, P in range, population size into 2. Obviously, we need to compute that 100 solutions. Now, out of 100, we need to compute the best 50 solutions here by implementing this crowding distance, implementing this non-dominated sorting and the crowding distance method. I hope that I should open that part here, then the things will be very much understood. Yes. So I think probably I should show you the algorithm also, then it will be easier for you to understand. Now let us see. So what I am doing here. So for P in range population size, firstly I am denoting this set as null and NP domination count as 0. Now let me show you. Then it will be much more clear. Otherwise you may not get it. Yes. So this was the pseudocode for that. See, exactly the same pseudocode here I will implement using this Python program. Exactly the same thing. I will not do any other thing. Exactly same thing. I see. For each P belongs to P, same thing I have done. S variable I have considered null. N variable I have considered null. This thing I have also considered. For each Q belongs to P. If P dominates Q, then we will add it into the list. Otherwise, we will update the counter list. Take it very clearly. Whatever I explained in the last session. Take it very clearly. Whatever I am doing. So this list I have defined. Yes. So here I put all the solutions which are dominated, and this is the counter S and P. Similarly, check it here. Whatever I have done, S and P. Okay. Now this one. For each Q belongs to P. If P less than Q, then this Q will be added to this domination list. Okay, SP union Q. If P dominates Q, add Q to the list of the set of solutions dominated by P. As we have seen here, I have explained everything here. That firstly, what we did, if you can remember. So firstly, what we did here. So quickly, once again I will tell you for this brief recap. See, this is our AS list. This is our N. So what we did. So for each and every solutions in the search space, that means out of 100 number of solutions we need to implement this. For solution 1, initially determine which are dominated by solution 1. 5, 4, 8, 3, 7, all these are dominated by solution 1. So these are included in this list. Yes. How many solutions are dominating the solution 1? None. That's why this is equal to J. I hope this is now clear. So this is my S, this is my N. I need to find out which solutions are dominated by each and every solution. Based on that, I need to update this list, S list, and also as well as this variables. Okay, so this was the pseudocode. This was the pseudocode for that. Okay, now let me come back to the program. See here what I have done. So for Q in range, population size into 2, that means from 0 to 99 out of 100. If see that whatever I have done. So how many fitness values I have? 2 fitness values I have. So one for the cost, second for the reliability. Check what I am doing. So when a function said to be dominate other solutions, so if value of cost like that, if value of cost once we are discussing in terms of cost, that means value of cost should be less and value of reliability should be more. Now let us check whatever I am doing. So 0 means what? P0 means what? This is the reliability, and P1 means what? This is the cost. See. So if first chromosome is less than value of the reliability is greater than the second chromosome. Take it very clearly. Take it very clearly. Whatever I am trying to write. This is my chromosome P. This is my chromosome Q. Check it. This is my chromosome P. This is my chromosome Q. Okay. 2 chromosomes and 3. This is my 2 lobes. This is my first for lobe. This is my second for lobe. So here P equal to 0 to 100, 0 to 99. Similarly here Q equal to 0 to 99. That means, so this is the first P, this is this Q. That means, so this Q means what here? So P means 1, initially P means 0, Q means 0, P0, P0. So that means here like that I'm going to do. That means P equal to 0, then Q will be 1, P equal to 0, Q will be 2. Okay, let us see. So 0, 1, first chromosome with second chromosome. So if first chromosome reliability is more than second chromosome reliability, check it. And first chromosome cost less than second chromosome cost. See here. These are similar. Or first chromosome reliability gets an equal to, because reliability of first and second will be equal now. And cost of second chromosome less first chromosome less than cost of second chromosome. See. Or cost is of this reliability is more and cost is less than equal. You can remember. I told when a solution will dominate other solutions. A solution will dominate other solutions. A solution, first solution will dominate the second solutions if for at least objective function. It is strictly better. And for all other objective function, what is happening? For all other objective function, that it is not worth. Then only we will say that our first chromosome, our first chromosome is dominating the second chromosome. So exactly the same concept I have implemented. Okay. So that means if this is the case, then what will happen? Let us say. I hope you are getting. Reliability is more. First chromosome reliability is more the second chromosome. Okay. And as well as cost of first chromosome is less than the second chromosome. Simply, if this is the case, then obviously. So we need, that means first chromosome. Now what is happening? First chromosome is dominating the second chromosome. That means I need to append the second chromosome, QS chromosome, into the list of this first one. Try to get exactly the same things here we are implementing. Okay. And if this is not like the case, that means what is happening? See, first chromosome reliability is less than second chromosome reliability. That means my first chromosome, in the first case, first chromosome dominated the second chromosome. In the second case, second in the this else second chromosome dominating first chromosome. Then we need to update the domination counter for the first chromosome. Take it very clear. What I said. Take it very clearly here. If P dominates Q, then we need to update Q to the list of SP. Otherwise, if Q dominates P, then we need to update the domination counter of the PSI. Standardly, so these things I have implemented using this Python code. Whatever I have again shown using the graphical presentation. Now let us proceed. Up to this point, it is okay. Next, what we are doing. So the same thing, that means for each and every chromosome, we need to implement it. As we have seen, for each and every chromosome, the same process we need to implement. Here you can remember that we have implemented the same thing for each and every chromosome. So yes, for each and every chromosome, we have implemented the same concept. Okay. So based on that, we are getting the list for these solutions and also the domination list and this domination counter. We are updating based on this process. Okay, next what we did, can you remember? Next what we did? So next we did after implementing this, see. So we find the first form. Which will be the first form? Where this domination counter is 0. That will be the first form. Again, on each element, again, yeah, for each element which are in the first form, I did the same operation. Yeah, I found that which element are dominated by this element and reduce that domination counter by 1. I did the same thing for the second element in the first form, reduce the counter by 1. Same thing for the last element of this first form, we reduce their counter by 1. Then, which are newly becoming 0. So, concluding this, I determine my second form. That means my next task is this. Let me check. So my next task is this. Yeah. See here. Here what I am doing. Take it very clearly. What I am doing. If NP equal to 0, that means P belongs to the first round. See, that means for which element the counter equal to 0, NP counter, domination counter for this, domination counter for this PF solution. So if it is 0, then we are putting the element in the first round. Take it very clear. Rank equal to 1, making the rank equal to 1 and putting that element in the first round. Yeah, so we are doing this for each and every element. So if domination count is 0, we are fixing the rank equal to 1 and putting it in the first round. That means the same thing now is implemented using Python program. Take it very clearly. So here domination counter equal to 0, NP equal to 0. Okay. So if domination, obviously, if this domination count equal to 0 for the PH solution, then the rank will be 0. That means it is the first non-dominated front. Now see here. So once the rank equal to 0, so simply we append it front 0 dot append PH solution. Take it very clear what we are doing. So exactly the same thing what is in the pseudocode. So that is in terms of Python. We are finding for each element this count equal to 0, considering those elements as rank 1, and we are appending all those elements in the front 0. That is our first. Okay, so first front is over. Next see. So once first front is over, then what we did? So for each and every element, here you can remember what immediately I explained, that for each and every element in the first front, we did the same thing. We check which elements are dominated and reduce their counter by 1. So let us check. Yeah. Here, what we did check. I equal to 1, initialize front counter. Why? If I not equal to null, that means my first front not equal to null. Some solutions are there in my first front. Q equal to null. Then for each P belongs to first front, for each solution belongs to first front. See, for each Q belongs to SP, that means what? For each P, which solutions are dominated by P? For each P, SP means what? Which solutions are dominated by P? Reduce that domination counter by 1. For each solution in the first non-dominated front, first front. For each solutions, which solutions are for the PL solution in the first front? Find out the solutions which are dominated by solution P. How to get it? So that are previously the list LKSP. So that means, so for all those elements from SP, so for each Q from SP, we will reduce the counter by 1. Yeah, see, exactly the same thing here I am doing. While front I not equal to null, I am declaring this null list for P in front I. See, Q in SP. SP means what? It's the list. Check it. SP means which solutions are dominated by P. Okay. So for every Q, okay, that are dominated by the PF solution. For every Q solution that are dominated by the PF solution, I reduce the domination counter by 1. Exactly the same things we are doing. Now, next what we consider. So for each and every element in the first round, we check it. So after checking this thing for each and every element in the first round, what we did? Again, we checked that which elements for which elements the domination count is becoming 0. See, if NQ equal to 0, that means rank will be 1. If NQ newly Q, now Q becomes 0. It will then rank will be 1. And then if Q not in Q, then you need to append it in that Q, and then you need to append it in the first round. So exactly this is a little bit difficult, but I hope I am trying my best. I hope you are also getting. So what we are trying to do here. That means for each element in the first round, we consider those elements which are dominated by this P. And then reduced their domination counter by 1. And if we find some elements newly where their domination count is 0, for those elements you put in the second front. You would run, this is the second front, and put all those elements in the second front, and continue these operations for each and every element in that list. So this is the pseudocode here. No, so this is the pseudocode, and yeah, this is the Python coding format. Next, the same thing, you incremented the value of I, you incremented, you are going for the next front. Okay, so like that you are doing. So this is our non-dominated sorting, how to implement non-dominated sorting using the Python program. So exactly the same thing now we have done here. Okay, next we'll proceed further. So our non-dominated sorting is open. Okay, so it will return the front. Okay, next. Next, what was there? Non-dominated sorting is over. Next, what was there? Yes, our non-dominated sorting is over. So that means here it will give us some set of fronts, like each and every front belongs to some set of elements. See here. So here we are getting 8 fronts. Okay, 8 fronts. So that means 8 fronts now belongs to 2n number of elements, belongs to 100 number of elements. Now we go for selection. See, this is the crowding distance selection. That means from this 2n number of elements, now we need exactly base n number of chromosomes. How to get it? See, this is one more interesting thing this is the crowding distance. See, population list, new population. This is the returning value. What we are doing? Selection. This is the function I will show you. Population size 50. Okay, from all front elements I am passing in this module, in this function. Population size, all front elements, and this is my objective function value in terms of reliability cost for each and every chromosome I have passed. And total number of chromosomes, the 100 chromosomes here I am passing to the selection function. Okay, now let us move to that selection function. So this is my selection function. This is the way to write down the definition of any function. You need to write df, then the function name, then the parameters. Okay, see, population size I passed there. Okay, population size. This is my chromosome objective function records, and this is the total chromosome that I have passed 100. Next, see here what I how interesting thing is here, very much non-dominated. Yes, crowding distance mechanism. Check. N equal to 0, new population. So we are making it now. We are making it now empty list. While n less than population size, see here. So initially I am considering that n equal to 0. So once again, quickly I will give you a recap of that, so to quickly understand it. What we did here, check it. Here, check it. So our first non-dominated sorting is over. So after implementing this fast non-dominated sorting, we are getting exactly to a number of solutions in all those fronts. Here we are getting in our solution 8 fronts. So all those fronts, if we take collection of all those elements, it will result to a number of elements, 100. So from this 100, we need to select base 50. See, yes. So here we need to implement this crowding distance mechanism. Okay. So now you know the crowding distance. So that means if we'll consider the elements from the first front, if it is less, direct length, so F3, we are finding if we take all elements from F3, the size will be more than N. Then in this front F3 only, we need to sort those elements based on the crowding distance. So that was the mechanism. Now let us see how to implement it using this Python program. Let us see. So now you are getting the purpose. So that's why initially I have written n equal to 0. Okay, so one by one, I'll take the elements, okay, from the chromosome list, total chromosome, I'll put it in that final n list. By n less than population size. For I in n, C, left front, that means So that what is the front size? My front size, my number of front is now 8. So okay. So I, that means 0 to 7. N plus this length, front I. Take it very clearly. Whatever I am trying to do. So front, ith front, that is my first front. First front, how many elements are there? Okay, that elements I am adding with n. Okay, suppose in my first front, 15 elements are there. Okay, those 15 elements I am adding it to n. So now my new n value is 15. Okay, let's see. Next, what I am doing. If n greater than population size, what is my population size? My population size is 50 only. And what is my right now my n? So based on my assumption, my n is 50. So it's not greater than population size. Okay, it's not greater than population size. Okay, so now suppose if it is not greater than population size, then directly we need to add. Okay, this is A, this is else. That means inside the new population, what we will do? We'll add. We'll add those values from the first front to the new population. See here, initially our new population is empty only. Water. Okay. So since n equal to 15, no issue. And directly add elements of the first front to the population. This is syntax for that. New population dot extend. Okay. First front over, let us say this first front over, second front over. Now we are coming to the third front. Okay. This is the magic here. We are coming to the third front. So let us say in the third front, what is happening? So now if I take all the values, all the solutions from my third front, then what will happen? Then size will be more than n, yes or no? As per my solution, as per my example, let us say if we move on third front and if we consider all elements from the third front, then values of n will be more than the population size. Let us say if this is then if n more than the population size, then what will happen? Then actually the beauty of crowding distance will come. We need to calculate the crowding distance. Calculate crowding distance. On the ith front element, that means by including that front, our total number of elements getting more than n. Only that front only need to do the required computation. Yes. So front type, that front only. So now we will do the crowding distance mechanical. Now let's move to that function, crowding distance mechanical. Front type, chromosome objective function values record. Okay. Let's move to this crowding distance. So this is our calculation for this crowding distance. That front and those corresponding objective function values here I have copied. Whatever I am doing, try to get it. For 0 in range 2, check it very clearly what I am doing. So this object, chromosome object record, see, M0, M in front, I see that. So the crowding distance computes the required sorting. See, it will compute the required, it will do the sorting of the solutions in the ascending order. Check it very clearly. According to their objective function values in ascending order. Okay, in ascending order of their magnitude. So here we consider that for the boundary solutions, in the last session I told, for the boundary solution, that means solution to the smallest as well as to the largest function value are assigned as infinite distance value. Boundary solutions we will not consider, we will assign the boundary solution distance as infinite. Let us see what I am doing technically clearly. So M, chromosome objects record in this M0 for M in front. It is very clearly what I am doing. So M in range 2. That means 2 values I will try to take it here. Take. M, chromosome object record. Here it is M. Okay, so that means whatever the 100 number of solutions we consider. So M, this is 0, take it. Yeah, so that's so from this, so for M in front means what? So in this, which front it is? So for our assumption, this is our third front, where the number of elements are more than the same if we consider that. So now those elements, what we are doing, let us say, sorted keys equal to sorted objective function key dot object. Key dot object, it means what? So based on these values, so we will sort. Okay, we will sort this object, whatever we got here. Take it here. So why I am telling this 0 equal to 1 to 2? So first is for the reliability, second is for the cost. Take it. First is for reliability, second one is for cost. For each and every object, for each and every chromosome here, two objective functions are associated. One is the reliability, second one is cost. Okay, one is reliability, second one is cost. So based on that, see here, 0. So first we will consider that 0 means 0, 0, 1 means 0. Once this O equal to 0, that means reliability. O equal to 1, that means cost. Okay, so here we are getting these values inside this object. Let us take it very clearly what I am trying to do. See. Next, what we are doing. So now we are sorting, we are just this, what about the key values we are getting? What about the object values we are getting? Objective function values we are getting. Simply we are sorting it. Next, what we are doing? Distance, sorted this key 0. Distance, sorted key is length. That means our first solution and our last solution. So those two solutions, for those two solutions, I am assigning the distance as impact. As I am telling, the distance of first and the last solutions will not consider crowding distance of first and last will not consider in our approach. That's why we have given our first solution as well as the last solution value to a maximum value. Let us see then what we are doing. For I in range C, front length, front minus 1. So what we are doing? If this length equal to 1, then what we are doing? Distance, sorted keys, sorted this. Now otherwise, so what we will do? Distance, sorted keys I, distance, sorted key I plus object. Why we are doing like this? So this is the function we are implementing here. Take it very clearly. So here, based on each and every objective function value, we need to compute the distance. I think last class I told one thing that once again I should tell, otherwise do that one. Yeah. So this was the fact for that. Let us take it. So what we are doing? So for the first, in that particular front, the first solution and the last solution, we are considering the distance to be infinite. Okay. Now what we are doing? Take it very clear. So take it. So this F max, F min, that is the maximum distance, maximum value. This is the minimum value for that objective functions. Okay. So that means I think we are considering the two things, just the previous and next. So those two elements, the difference between the objective function value and divided by this objective function value maximum, objective function value minimum. So these operations we are performing for this crowding distance method. So exactly the same thing here I have implemented using this crowding distance. Take it here. Whatever we are trying to. Let us come back to our. This is a little bit difficult coding. Let us come back to our coding. Whatever you are doing, check it. Whatever you are trying to do here, check it very clear. So the same thing what I told. See. So this is the distance. How I am updating the distance? See. By using the objective function values of the sorted keys, keep this I plus 1, whatever you have seen in the pseudocode, I plus 1 minus this I minus 1. Okay, divided by this objective function values, this This front minus I, and this is 0. -1 and 0. Take it. Whatever you are doing, very clearly take it now. This is once again I say, so this is sorted key check. So this is sorted key 0. Okay, and this is the sorted keys. Let us check how we are getting the sorted keys. Here we are getting the sorted keys. Here we are getting the sorted keys using this mechanism, using this coding. So that means, so here whatever you are trying to do. So for each and every solutions based on their objective function values, so we are updating that particular the distance, crowding distance for that particular solution. Let us check what will happen. That means for each and every solution, it will determine a distance. So based on this formula, whatever I have written here, so each and every solution will return some distance. And entirely this depends on the objective function value. As I was telling, so whatever I was computing using this, entirely this depends on the objective function value. Here we are using a bi-objective, two-objective optimization. That means we have two objectives. If it is three objectives, this process may be a little bit complex. So here, whatever we are computing, so we are returning the distance values for each and every solutions based on this formula. Okay. So now, so once distance has been returned, now let us see. We'll move to this crowding distance. How to try to our crowding distance? Let me check. So my crowding distance now. The selection. Okay. Crowding distance. This selection, yes. So here I have got the crowding distance. Okay. Based on that, I have got the crowding distance. So based on the objective function values of each and every solutions, here we are deriving the crowding distance. Next, we are implementing the sorting based on the crowding distance. Implementing the sorting based on the crowding distance, then making it in reverse order. First maximum, next minimum. Next, see what we are doing. Take it very clear. If J in sorted this crowding distance function, if length of this less than population size, see, then we will break. So that in that process, what we did. So if n was more than the population size, we computed the crowding distance. Here we have in descending order, we are giving the crowding distance. Next, what we are doing? Next, only those values we will get. So, by which we can fit our final solution to exactly n values, exactly 50 values. It is very clear. If length of the new population equal to population size, obviously we will break. Otherwise, you need to update that new population. That's what we are trying to do here. So that means once in some front, our number of values are more than n. So on that front only, we will implement the crowding distance mechanism. And those elements which are having more crowding distance, only those values will be added one by one until unless the size fits to 50. Once it is 50, simply then we will break. Okay, so ultimately now whatever we are getting, so we are now from that, ultimately we are getting from 2n to our n number of solutions by implementing this crowding distance mechanism. So it will return? So it will return the population list as well as this new population. Okay, population list means the previous one, and new population means what we got right now. These two things it will return. Let us come back to our main function. Yes. So population list, new population. So we are getting these two by implementing the selection. That means we implemented in turn the crowding distance mechanism. Okay, then what we are doing? What we will do? So if n equal to 0, see that base list, that means whatever the population list we are getting, that is the base list if n equal to 0. See, otherwise, see what will happen? Total list, population list plus base list. Base list, what we are getting? Check. So by implementing this routing distance mechanism, here we are getting two things. So we are getting that n number of solutions from 2n by implementing the environmental selection, that is by implementing the non-dominated sorting as well as the crowding distance, we got exactly from 2n number of solutions to n number of solutions, from 100 solutions to 50 solutions. That we got. Now can you tell me what will your next step? Again, so if you can see, if you can follow the flow chart, what will be the next step? See here. So again, so this part is over. This part is exactly over, which was main related to this crowd distance, related to our NSDA2 environmental selection. Next, we have got QT, okay, that is that population, and also QT, parent population as well as new QT populations. Here, from here, we will get PT, PT will get QT. Again, so this will be a combination of PT and QT, parent solution as well as the child solution, offspring solutions. The same thing here, they are already written. Again, so I'm not going on to this slide, which I will bring here. I will try to conclude it. So now this is the results. So here we are getting as a result, we will get the base list as well as the base object. Now see here. So here already we are getting the results. See, we are getting some chromosomes. See here. So these chromosomes. So now this is the our ultimate result we are getting. And so first one is the reliability, and second one is the cost. So this one we are getting as the best solution here. So here basically we got a number of solutions. So what I did particularly, as I said, that multi-objective optimization will give you a number of solutions in turn. And from those set of solutions here, again I implemented the crowding distance mechanism that actually given here. Okay, again I implemented the crowding distance mechanism, and I have collected. I have found that this is my best solution, best chromosome, and this is the best chromosome, and here I am getting what is the reliability and what is the cost of my best chromosome. This is the time. Okay. Now here I will skip this one. Yeah. So here I will show you one thing. Yes. So that was our initial solution. See that. Now this was our final Pareto optimum front. Okay, from where we are trying to get the final solution. This was our actually what the problem we have done. So this was the initial 100 number of solutions. From that we are trying to get the Pareto optimum front, which may look like that. And as we consider that from, as you have seen, that in the Pareto optimal front, that is the so in the Pareto optimal set of solutions, so none of the solutions will be dominated. This is a non-dominated solution set. None of the solutions should be dominated by each other. So now we need the user needs some domain knowledge, some expert knowledge to select any solutions out of that based on some requirements. Now recently, so what we are trying to do, so actually NSDA2 tells up to that pattern. Now we are trying to apply some multi-criteria decision-making mechanism here on this non-documented sorting on this Pareto optimal front, whatever we are getting by implementing the NSDA2. And using that multi-criteria decision-making technique, we are trying to find out that which one probably will be the better solutions, because number of solutions are here now. Number of solutions are here. NSDA2 is telling you can select anyone based on the domain knowledge. But here, what we are trying to do, that not one based on the domain knowledge, we are trying to find out that out of these 50 number of solutions, which solutions may be preferable. So we need to find out using some other mechanism, that is MCDM techniques. And here in our experiment, so we have used some MCDM techniques to try. We are trying to find out which solutions would be the better quality solutions. So here we have used some techniques. So my next codings are like that only. Anyway, so that is not about of our discussion part today. But today, what about the things I wanted to discuss? I hope that participants now you are getting the thing. Actually, it was a difficult task. You know, micro-objective optimization it is the most difficult part. Once you write some program, writing a program for genetic algorithm is very much easier. But once I'm writing some program for multi-objective optimization, it is really difficult. It is very much hard to write a program. Actually, I have the complete program, but whatever I have shown you, some snapshot of that main program only, because it will take too much time to explain. That's why I have not explained the natural selection part. Also, I have skipped some part, and also I have explained very briefly some of the sections. But I hope that what was my intention, that you will understand this Python implementation of multi-objective optimizations. At least those who know the Python programming, I feel they will understand it better. Those who are little bit, I think, yet to know, yet to learn the Python programming, for them it may be little bit difficult. But again, I believe that you will get some idea, and this idea may be helpful for you to develop some Python programming for to solve this multi-objective optimization kind of problems in future. Yeah. Yes. So just installing stop presentation. Yeah. Yes. So that is all about from my side for this session. Now I will be ready to take some questions from the participants. Yeah, I think both of the coordinators are there, Manjubala Madam and Sanjay Kumar Panda sir. Anyway, so now I want to convey my thanks to the participants once again to listen to me today for this last 2 hours. Actually, it was a typical coding explanation. Participants really thankful for to the participants for having the patience during my presentations. Actually, as I told that explaining complete multi-objective optimization is very much difficult and also it is very much time consuming. So what I have tried my best to briefly explain the most important part of this multi-objective optimization, particularly NSGA2, multi-objective genetic algorithm. So now I'll be ready to take any questions. So if there is any other questions. In my last sessions, already I have communicated my email ID and contact number. So participants, so please feel free to communicate in my email ID as well as in my contact number, although if you have any queries in future. Now it's over to Madam and over to Sanjay Panda sir.
Thank you, sir. Thank you very much.
Okay, so thank you, Madam.
Thank
Thank you,
you.
Sanjay Panda sir. So again, once again
Thank you, sir. Thank you.
for giving me the opportunity to deliver my thoughts in this exhibit. Once again, thanks to everyone.
So we'll start the next session at 5:15. Sir, namaskar, sir. Sir, namaskar. Sir, mute ଅଛି ଆପଣଙ୍କର microphone, mute ଅଛି.
Hello,
Sir,
am I audible?
Yes, sir, yes.
Huh?
Yes, sir.
Okay, okay.
Namaskar, sir.
Namaskar, namaskar, namaskar.
Sir, namaskar, sir.
Namaskar, namaskar, Sanjay.
Sir, start करिया?
Department ରେ ଅଛନ୍ତି sir?
ଏବେ ଜଷ୍ଟ କ୍ଲାସ ଥିଲା ତ ଏବେ ପହଞ୍ଚିଲି ଡିପାର୍ଟମେଣ୍ଟ।
ଏବେ department ରେ ନା sir?
ହଁ ରୁମ ରେ ଅଛି ଡିପାର୍ଟମେଣ୍ଟ ରୁମ ରେ।
ଆଚ୍ଛା ଆଚ୍ଛା ଠିକ ଅଛି।
ମୁଁ ସେ ଫାଇଲ ଟା ଖୋଲୁଛି ହାଁ।
sir.
ଓକେ। ଠିକ ଅଛି will be in touch.
हाँ सर yes sir
ओके। थैंक यू टाइम बाहर କରିକି ଆସିଲା ଦେଖା।
thank you sir मैं राउंड नहीं आता सर असले असली बैठ ठीक है
ऑल द बेस्ट।
thank you sir
କପି ଥିଲା ଯେ କ୍ଲାସ ରହି ଗଲା ତ।
हाँ सर क्लास कर सर
କାଲ ଅଛ?
आज कल ऑनलाइन हाँ सर सीधे टाइम में
ଅଲଗା ମାନେ ଏଇ ଫୋନ ରେ କଥା।
हाँ
ठीक।
वो से समझ सर सब ले लाइन ऑनलाइन नहीं रहो सर ये कोविड में पूरा क्लासेस ऑनलाइन होते हैं
ନା এখন কোভিড নাই না।
हाँ नहीं कोविड में
এটা অনলাইন ক্লাসটা।
Sir, start करिया?
ହଁ ମୋର ଦେଖା ଗଲା କି ସ୍କ୍ରିନ୍ ଟା ଦେଖିଲ?
ना ना sir.
ଦେଖା ଯାଇନି?
ना.
ର ଖୋଲୁଛି ର ଫାଇଲ ଟା। ନା ସ୍କ୍ରିନ୍ ଟା ଦେଖା ଯାଉନି? ଏଲୋ ଖୋଲି ତ म्यूट सिलेक्ट एंटायर स्क्रीन एलो एलो देखा गला?
Yes, sir.
हेलो?
हाँ sir,
हैं?
देखा गला sir.
ओके ओके
1 minute sir.
हां लेट अस स्टार्ट।
Good evening all. I welcome Professor Saroj Kumar Patel sir to this session. So in this session, sir is going to discuss about single variable optimization techniques. So it's my privilege to introduce Professor Saroj Kumar Patel sir to our participants. So sir is currently working as a professor in Mechanical Engineering Department of NIT Rourkela. So in this institute, sir has discharged various responsibilities like Dean Academics, Dean Student Welfare, Registrar, Chief Warden, Head of Training and Placement, Head of Central Workshop. Sir was also Project Officer, NTMIS, National Technical Manpower Information System for the entire state of Odisha, handling all the government and private engineering colleges, engineering diploma schools and pharmacy colleges of the state. So, sir completed BTech in Mechanical Engineering from NIT Rourkela in the year 1985. Initially, he had industrial experience with Hindustan Aeronautics Limited, Koraput Division, for 5 years before joining NIT Rourkela. Sir obtained MTech degree from IIT Madras, PhD degree from IIT Kharagpur. His broad area of academic interest are optimization, statistical quality control, operation management and machining. Sir has supervised more than 10 PhD theses. Sir has published more than 75 quality research articles in peer-reviewed international journals and more than 60 conference proceedings. Sir has published 3 textbooks on topics like basic statistics, operational research, and MATLAB. With this brief introduction, I welcome once again, sir, to our program, and it's over to you, sir. Please start yours.
Okay. Thank you, madam,
Thank you, sir.
for giving my introductions. So all those whatever you told are all are past. I am now professor in mechanical engineering in NIT Rourkela. So let me thank Professor Manjuwala for giving me this opportunity to share whatever knowledge I have in the field of optimizations in this refresher course. So how many participants are there, madam, in today's class?
Today I
Hello?
am joined only 25, I think 23 or 24. There are 70 participants are there. In our
Okay, no problem. So at least 25 participants are there,
Okay.
and their what is their background? Means are they PhD scholar or they are faculty or
Faculty,
what?
sir. Some are faculty, PhD scholar, mix, sir.
Okay, thank you, thank you. So the topic whatever I'll be teaching covering today is on single variable optimizations, and in tomorrow we will discuss the multivariable optimization, how we'll optimize. So this is my email ID, skpatel@nitrkl.ac.in. So all the participants are welcome, encouraged to interact with me at even after this end of this refresher course on any doubt they have, whatever that we'll be discussing in today's and tomorrow's classes. So either through email or through WhatsApp. My WhatsApp number is given here, 9437484951. Also, whatever we will discuss in today and tomorrow classes, most of this video lecture with also the other lectures related to optimizations are also available on YouTube. So this is that link for my YouTube channel. So all the participants are advised to subscribe to my channel so that they will be getting access to the video lecture on this related to optimizations. Besides these optimizations, also I have another list of video lecture related to optimization related to problems. All those operation research techniques like linear programming, CPM and PERT, queuing theory, scheduling. Also related to that, also you can find the video lectures on my YouTube. So for today's class, if you want to understand, this is basically all whatever will be taught has been taken from this book, very simple book, but very fundamentals. Any beginners, if you are starting on optimization course, this is the best book to start with. Very easy to understand. This is written by Professor Kalyanamaya Dev, Optimization for Engineering, Design, Algorithm and Examples. Publication is Prentice Hall of India. So Professor Kalyanamaya Dev was a professor in IIT Kanpur in the Department of Mechanical Engineering. Now, of course, he is in some universities in USA. So he is an expert in optimization field. This slides gives you the other list of books related to optimizations. And one of this book is co-authored by me, where you can find the MATLAB codes for the single variable optimization algorithm. It is the first book. This slide is also few of the books related to optimization. Now this is the book co-authored by me, where you can find find the MATLAB code for all the algorithm for optimization of single variable unconstrained problems. This is another book co-authored by me related to operation research, and another my book that is on basic statistics. Okay, let us come to, is the slide visible? Now I am at page 8. Please confirm.
Yes, sir, visible, sir.
Okay. So slides are moving correctly. Okay. So any optimization problem, when first of all is that given a problem to you, you must first mathematically formulate it and write down in a mathematical expressions before applying any algorithm. So any optimization problem, when you formulate mathematically, it looks like this. It has consists of three main parts. The first line that defines the objective functions, that is f of x1, x2 up to xn. This x1, x2, xn, there are n unknown variables. And when you solve an optimization problem means you have to find out the values of this n unknown variable. What will be the value of x1? What will be the value of x2? Like that for xn. Such that when you find out the value of f, the objective functions f, the value should be either minimum or maximum. So an optimization problem will be of two types depending upon what is your objective. If the objective is to minimize, it will be a minimization problem. So this slide shows a minimization problem. And almost same, only thing is that the first word, if you write maximize instead of minimize, that will be a maximization problem. Of course, with the corresponding changes in the sign in the constraints. Okay. So the first line, first word should be written either minimize or maximize, followed by the word f of that function, objective functions, f of the unknown variable x1 to xn. Then come the second part where we list down various constraints, means all these expressions should be satisfied. So subject to all the constraints. Now these constraints can be classified into two groups. One is that constraint having a symbols inequality. So this is called inequality constraint from B1 to Bm. And there may be also constraints where you can find out equality. So these are called equality constraints. So whether it is inequality or equality, the left-hand side will be again a functions, just like objective function, here will be constraint functions. And on the right-hand side, there will be numbers, denoting that availability of resources, right? So B1 to Bm, these are all numbers. Similarly, D1 to Dp are also number. So in this case, we have m number of inequality constraints. So accordingly, the right-hand side number varies from B1 to Bm. And on the left-hand side, these are m number of constraint functions. So each of the left-hand side is a function of again that n unknown variable. But of course, some other function, that is G1 function to G2 up to Gn. So G is the inequality constraint functions. Similarly, H denotes on the left-hand side the equality constraint functions. And the corresponding number is D1 to Dp. Now the last line, that is the third part, that denotes your search domain, in which range of x1, x2 up to xn, each of these unknown variable, in that which range you should search for the value such that f value will be minimum. That means for every unknown variable, there is x1, x2 up to xn, we have to specify their lower limit and the upper limit. So for x1, the lower limit is x1L, L for lower, and the upper limit is x1U, x1 upper. Similarly, for x2, we should search it in the range x2L to x2U. Similarly, for the other variable. So this is the mathematical formulations for a minimization problem. Now, next slide will maximize. In that case, we'll see only two changes we'll find. That is, instead of minimize, it will be maximize. And in the inequality constraint, instead of greater than equal to, it should be less than equal to. Otherwise, it is same. Same three parts, but it is maximization problem. So these two constraints, that equality constraint having h functions and inequality constraint, G function, these are actually called functional constraints. And if you observe the last line, that is a search domain where for every unknown variable, we have a lower limit and upper limit. So here also it is a constraint, means X should be, it has to satisfy two constraints, means X1 should be greater than XL, X should be less than XU. So that's why this is also one sort of constraint. We call it side constraint because it defines the lower side and the upper side, right? So again, this f is objective function, x1 to xn is your design variable or your unknown variable, whose value we have to find it out. And this g to gm and h to hp, these are all constraint functions. And these are in constraint functions. So these are the major parts you'll see the constituents of an optimization problem. Now let us classify all those optimization problems. If we have only one objective, so this is single objective optimizations. But if we have more than one objective, it will be multi-objective optimization. That means if, let's say, we are trying to maximize the let's say the metal removal rate, which should be as far as possible, you have to cut it. But at the same time, you have to also observe that the surface roughness, if you want to minimize, so maximize the metal removal rate, but minimize the tool wear rate, like that. So two objectives. So that is multi-objective. But if you have only one objective, let's say we want to maximize our production rate or maximize the profit, so then it will be single objective. Okay. If you have only one variable, there is unknown variable, there is value of n, small n is equal to 1, then it will be single variable optimizations. So today we will discuss single variable optimization problem. And in tomorrow's class, we will discuss multi-variable, where the number of variable is more than 1, x1, x2, or if it is 3, x1, x2, x3. Now, subject to constraint, in some of the problems, there may not be any constraints. So there is no question of G function or H function. So that will be called unconstrained optimizations. But if there are constraints, it will be called constrained optimizations. Now, depending upon the objective, it can be a minimization problem. If the objective is to minimize the total cost of production, so minimization problem. Or if your objective is to maximize the total profit, then it is a maximization problem. Now, depending upon the expressions, that is in the objective functions or in the constraint functions, it can be the linear problem, where the maximum power of any variable is 1. Linear problem means the equation would be like this: 3x1 plus 2x2 plus 3x3, x1, x2, x3. There is nowhere x1 square or x1 cube is there. But if it is not linear, then it will be non-linear. In the non-linear, the power of an unknown variable may be other than the 1, or it may contain sine, cosine, logarithmic function, etc., etc. It is not linear. Now, depending upon the value of the this one, that whether the values of that unknown variable is an integer, means let's say your objective is to decide how many number of let's say it is an automobile factory. An automobile factory, it is producing different models of car. So you have to decide how many number from which brands of car you are going to produce in the next production year. That means from Maruti Jain, how many you have to produce, or Baleno car, how many you have to produce, that Maruti company, that Suzuki, Maruti Suzuki, how many number from which brand has to produce. So there cannot be, we cannot say that it is 2.5 car to be produced. It has got no meaning. Either you have to produce 2 cars or 3 cars. So there is integer programming. But if it is a cement manufacturing industries, so where you can produce either 10 kilo of cement or 10.5 kilo of cement, it has some meaning. So there it is real value. It can take even the fraction value, or there can be combination of both. There is a mixed integer programming problem. Now, if all the decision variables are independent of each other, this is a static problem. But if the decision variables, some of the decision variable are the function of other decision variable, so this is a dependent decision variable, that is dynamic problem. Now, coming to the solution methodology, we can have traditional method or non-traditional method. In traditional, we can have analytical method where we can use that calculus. There is a derivative. There is, you take first derivative, then higher order derivative, second order, third order. Whatever the solution we get, the minimum values and maximum value, this solution is exact solutions we'll get. So there, the accuracy that we'll obtain will be 100%. So that method is called analytical method. But this is helpful only if our objective function is simple. We can able to find out the derivative very easily. But if, let's say, the objective function is very complex, finding its derivative is not possible, or it is a discontinuous, let's say, functions. So finding derivatives is not possible. So thereby we have to, but we can still solve that problem iteratively. And that method is called numerical method. And numerical method, please note it will never give you there is no guarantee that it will give you the 100% accurate result. It will be approximate. It always gives the approximate solutions. So depending up, so here we will be defining that up to what accuracy we want the solutions. So accordingly, it will solve and give you the solution. So if possible, it is always advisable that we should solve it analytically so that you can get 100% accurate result. If it is not possible, we have to solve it numerically to get approximate solution. And these days we are also following non-traditional methods. That is all nature-inspired numerical methods. That is on the basis of the phenomenon that we observe in the nature. Accordingly, the algorithm has been devised and that methods are being used, just like your genetic algorithm or simulated annealing, etc., etc. So these non-traditional methods, also called as meta-heuristics, can be classified into 5 groups: evolutionary algorithm, swarm intelligence algorithm, physics-based algorithm, human-based algorithm, and other nature-inspired algorithm. In the evolutionary algorithm, which is based on this biological evolutions of organisms, the methods are genetic algorithm, genetic programming, evolutionary programming, etc., etc. Some species, they search for their food always in a groups. Like you'll find always the groups of birds or groups of fishes, groups of ants, no, groups of bees collecting the honey. So accordingly, based on their hunting behavior, searching for the food, this algorithm has been devised. Particle swarm optimizations, artificial bee colony, ant colony, etc., etc. Then on the principle of physical rules that is observed in the universe, there is simulated annealing, there is mimicking this heat treatment process, gravitational local search, Big Bang Bing Crunch, gravitational search algorithm, etc., etc. This is also the other physics-based heuristics. Then human-based heuristics. There is how the human behaves, like how the teachers teaches the classes and the students learns it. On that basis, an algorithm is their teaching learning-based optimizations. Jaya algorithm, harmony search, taboo search, etc., etc. This is also human-based heuristics. Then other heuristics can be invasive weed optimization, memetic algorithm, monkey search, etc., etc. Now let's come to our single variable optimization problem. In that, we will begin with very simple problem, and we will begin, we'll refresh our knowledge. Whatever we have already learned in our +2 level, that using how we can use derivatives to find out the optimal solutions. So please tell me, so this is an example, let's say, identify the local maximum, local minimum, maybe one or more, and then point of inflection for these functions. Yes, can anybody tell me how we can able to solve it? Yes, from participants. use
We
your
will
plus.
take a first derivation. Taking first derivation equals to 0, we will get the values of x and then put those values in the second derivation. And we will get to know
Very
whether
good.
it is maximum or minimum.
Yes. Yes, yes. Very good. Very good. So here the rule says that first find out the first derivative f dash x and will equate to 0. And this we solve it, right? And whatever value x will get it. So you can say that at that x, the values of f will be either maximum or minimum or point of inflection. But whether it is maximum or minimum or point of inflection, to differentiate that, you have to take then higher order derivative, second derivative, third derivative, like that. And you keep on take higher order derivative till you get a non-zero value at that particular values of x at which the first derivative was 0. Let us note down that what is that you keep on increasing it, and for the first time you will get a non-zero value. So that's the lowest order of n. So this n is the order of derivative. So it can be 2, 3, 4 like this. Yeah. Now this n can be odd or even, right? If this n is odd, then that x value, at that x value, f will have point of inflections. We will discuss what is point of inflection, which is neither maximum nor minimum. So if it is not odd, then this n will be even, right? So in this even, we will have a local optimum. Optimal means it can be either maximum or minimum. Now, whether maximum or minimum, to differentiate that, we have to now compare their values. So this nth order derivative at that x, that value will be either positive or negative. If it is positive, then at that x value, the f will have minimum value. So that x will be a minimum point. Local minimum will be at that x. But if it is negative, that will be maximum point. So this is the rule that already we have read it in our +2 level. Any doubt? We will use this rule and solve that problem. But so far as this rule is there, please read it, and any doubt if you have. Please respond yes or no. I know I'm not able to see you, right? So you have to time to time you have to respond it so that I can able to know that whatever I am telling is audible to you at least. At least one, please respond.
Yes, sir.
Okay, thank you. So no doubt, right? So now let us solve it. So that for that problem, f of x is x5 minus 4x4 plus 3x3 plus 2. So first derivative will be x for 5x x5, it will be 5x4 minus, for x4 it will be 4x3, so 4 into 4, 16, so 16x3. For x3 it will be 3x square, so 3 into 3, 9, so 9x square, and for 2 it is 0. Now this first derivative we have to equate to 0 and solve it. So let us solve it. So 5x4 minus 16x cube plus 9x square is equal to 0. Taking x square common, we'll have inside the bracket 5x square minus 16x plus 9, right? So this gives us that either x square is equal to 0 or whatever is there inside this bracket, this factor, there is 5x square minus 16x plus 9 is 0. So when you solve x square is equal to 0, we get x is equal to 0. So this is one values of x where the function f will be optimal, right? And also we have two more values because this is a quadratic equations. So using that formula minus b plus or minus b square minus 4ac divided by 2a, we get 2.472 or 0.728. So thus we have total three values of x that is shown in blue color, that is 0, 2.472 and 0.728, where the values of f will be optimal. Optimal means there are again three cases, either maximum or minimum or point of inflection. Now let us test that. So to do that, we have to find out higher order derivative, second order, third order, till we get a non-zero value. So we get 3 optimal point, as I told you. Now, higher order derivative will be, the second derivative will be 20x cube minus 48x square plus 18x. And third order will be 60x square minus 96x plus 18. We can go up to fourth and fifth also, but let us first now check whether we are getting non-zero value at second and third or no. Otherwise, we have to go to even fourth order or fifth order. Okay. Now let us put these values. So we have 3x values, 0, 2.472, 0.728. Now put the value at 0. So at x is equal to 0, when you put it, the double derivative will be how much? 20 into 0 minus 48, 0, so this is 0, 0. So this will be 0. So we cannot stop it here. This is not a non-zero value. So you take the higher order, that is third order derivative. That is 60x square minus 96x plus 18. So now here, now you put the value of x is equal to 0. So when you put x is 0, so first two terms become 0. We are remaining with 18. So for the first time, we get a non-zero value for the derivative at x is equal to 0. Now, this 18, which is non-zero, is occurring for the third derivative for the first time. And before that, it was 0. Even the first derivative was also 0 at x is equal to 0. So now n is equal to 3. So 3 is odd. So that's why at x is equal to 0, the f is a point of inflection, neither maximum nor minimum. Now let us test for other 2 points. So 2.472. So put here at the double derivative. Have you brought your calculator or Excel or anything? The laptop or even mobile phone if you have calculator? Please calculate and tell me whether you are getting 53.3 or no for the double derivative. Put 20 into 2.472 to the power 3 minus 48 into 2.472 plus 18 into 2.472. Are you getting 53.3? Check and tell me. Are you doing it? Hello? Are you calculating it?
So actually, I'm traveling. I'm going from my workplace to my home.
No problem. But others, what about the others? Hello? Others, please respond. Otherwise, I am speaking to some vacuum. I am feeling like vacuum because I am not able to see you.
Yes, sir.
Yeah. So did you get 53.3? Anyone? Did you get 53.3? Please respond. I am not able to hear anyone. Are you there, anyone in the class?
Sir, in the chat box they mentioned, sir.
Yes, sir. We are.
Okay, good. So since we got already a non-zero value, that is 53.3, we need not have to calculate for the higher order derivative here, right? So here the value of, we stop here. So n is equal to now here 2, because at the second order derivative we are getting a non-zero value. Okay. So it is even number. So even number means either maximum or minimum. But since this 53.3 is a positive value, so we can say that f will be minimum at x is equal to 2.472. Similarly, at x is equal to 0.728, when you put it, you will get the double derivative value will be minus 4.6. Since it is negative value, and this is a non-zero, we stop it. That is at the second, n is equal to 2. That is an even number. So this we stop, and this minus 4.6 is a negative value. So we say that 0.728 is a maximum point. So this is the way we can find out all the peaks of this curve: maximum point, minimum point, and also the point of inflection. And whatever the result we get, that is 0, 2.472, 0.728, these are the 100% accurate solutions. Similarly, you can solve for this. Another example, you can solve it at your home. I'm just going same procedure. So I'm just giving you, you can try. This is just like an assignment for you. You can try at your home. So here also, we take first derivative equate to 0. And then we factorize it. You can try at your home. You can factorize it step by step. And then finally, we can get that it is a product of three factors: x minus 3 into x minus 2 into x minus 1 equal to 0. So when you solve it, we get three solutions for x: 1, 2, and 3. That means f will have three optimum values at 1, 2, and 3. But which is maximum, which is minimum? To find out that, we have to find out the higher order derivative. Now, if you are using MATLAB, instead of doing the factorizations, the solutions, that finding the root of an equations can be very easily done using the function called roots. So before that, you define this matrix X, that is nothing but a vector of all the coefficient in the decreasing order of this power. So for x3, the power is 1. So this first element will be 1. x3, then next power is x2. So coefficient is minus 6. So write down next element will be minus 6. Then next is x, corresponding to 11. So plus 11. Then there is no x here, means x2 are 0. This coefficient is minus 6. So 1, minus 6, 11, and minus 6, you write down in a square bracket, then you put equal to 0. So this you enter it in the MATLAB. And then this is a command prompt for the MATLAB, 2 greater than symbols. In that, write down the command roots within simple bracket, this vector x. Then the result will get 1, 2, 3. That means x is equal to 1, x is equal to 2, x is equal to 3. The same thing, we can use the MATLAB to find out, to solve the first derivative equal to 0, or any equations equal to 0, you can solve it and find the roots. So please note it here, it is not root, it is roots. The name of the subroutine is roots. Okay, so first derivative is this, second derivative is this. Then at 1, 2, 3, you have to find out the values. So at x is equal to 1, the next higher order derivative, the double derivative is 24. Already it is non-zero. So n is equal to 2. And this 24 is a positive number. So we can write down that x is equal to 1 is a local minimum point. Let us test at x equal to 2. At x equal to 2, we get the double derivative itself a non-zero value. So we stop it there. And this non-zero value is minus 12, which is negative. So that's why you can write down that x is equal to 2 is a local maximum. And at x is equal to 3, the second derivative is plus 24, again a non-zero value. So we stop. That is n is equal to 2, that is even number. And this 24 is a positive number. So that's why x is equal to 3 will be local minimum. So for this problem, we'll have 2 local minimum and 1 local maximum. So this is the way we can find out the optimal solutions analytically with 100% accuracy. Now this is, see, this function, if you plot f of x versus x, as x increases, initially the f value decreases, then becomes minimum at this point, and then further if you increase, it becomes increases. So this point, the bottommost point represents local minimum, and this is the topmost point represents the local maximum. That means as x increases, it first increases, reaches to the maximum value, and then decreases. But if you take combination of these two, means 1/2, if you see from here to here, it looks you have taken it from a local minimum, and from here to here, this person, it has been taken from local maximum. So combination of maximum and minimum, if this is the case like this, then this point will be called point of inflection. So if this is concave upwards for a local minimum, this is convex upwards if this is a maximum point, and at point of inflection this is neither maximum nor minimum. Okay, for a functions there can be many ups and downs. So here there are 3 peak point where the values of f is maximum, 1, 2, 3. So each one of these is called the local maximum point, means in their locality, in their neighborhood, they are maximum. So in this neighborhood also, this is maximum. This is in the neighborhood, this is maximum. So we have 3 local maximum. But for the entire search space, there can be only one global maximum. That is maximum of all local maximum is called global maximum. So this is the global maximum, whereas these are the local maximum. Similarly, in this example, there are 3 bottommost points representing 3 local minimum points, but out of which the minimum of minimum is this is your global minimum. This is the out of all these values in the search domain, this is the where that value is minimum. This is called global minimum. So in the entire search space, there can be only, if there is a maximum value, one global maximum and one global minimum. Whereas there can be many local maximum and many local minimum. Now coming to numerical methods, these are all whatever you have learned is the analytical method where you get 100% accurate data. Now if we are not able to get analytically, solve it analytically, we can take the help of the numerical method. So where it is solved iteration after iterations. So for if the number of variable is 1 and there are no constraints are there, this is unconstrained problem, then all the algorithms can be classified into 2 groups. First group is direct search method, where we need not have to take any derivative or approximately derivative also, we do not take the help of this one. So under that we have exhaustive search method, bounding fetch method, interval hopping method, Fibonacci search method, and golden section method. Main other methods are also there. In gradient based method, second group, where we take the help of gradient. Gradient means derivative. So if derivative we are not able to find it out, then approximately also we can take the approximate values of derivatives can be taken numerically. Okay. Under that we have Newton-Raphson method, bisection method, second method, cubic search method. Now if the number of variable is more than 1, again we have 2 broad groups of methods. In gradient based method, we have Cauchy's steepest descent method, Newton's method, and Marquardt's method, where we'll be taking the help of gradient or derivative. But without derivative, the methods comes under direct search method. So these are simplex search method, Hoop-Chips pattern search method, Powell's conjugate direction method. So whatever the method that we listed down in the previous 2 slides, that comes under unconstrained optimization method. That means when we have only objective functions, but there are no constraints. But if there are constraints, then the methods that we showed, numerical method that are suitable to be used are penalty function method, method of multipliers, variable elimination method, and other methods are there. Frank-Kolb method, cutting plane method, etc. Now let us begin numerical method for single variable unconstrained optimization problem. So this is minimum point, and all the algorithm we will discuss here in this class is to find out a minimum point. But all those algorithms can also be used to find out a maximum points also, because just to by modifying our objective function. That is, whenever you say maximize a function f, it's nothing but minimize minus f. So algorithm to minimize can be used and solve the maximum problem. Now minimum point is find out in two stages. In the first stage, we just find out tentatively what is that interval. We just identify in which this minimum point is lying. So since we are finding out the interval or the bracket having a lower bound and upper bound, so these methods are called bracketing method. And in the second stage, depending upon our desired accuracy, we use somewhat better method, a more efficient method to find out, to locate the optimal point. So under bracketing, we have two methods: exhaustive search method, also called as equal interval search method, because there we search exhaustively. We start from the lower bound, and at every equal interval, we find out the values of f, we compare it, and then we proceed further. So here the step size is always same. At regular interval of some step size, we will be finding out, we will be searching for the minimum point. But in bounding pitch method, this interval is not same. Rather, it exponentially changes. Let us discuss now the algorithm, the simplest algorithm, exhaustive search method. So here we assume a initial search interval, search domain u to v. That minimum point is lying, let's say, arbitrarily we say an interval you take u to v. And this is u to v. And this interval, since we have to start from the lower bound, that is u, and then we have to search at various points. And these points will be at numerically at regular interval of time, regular intervals, we have to find it out. So from here to, so this entire interval, we have to divide it into n number of equal parts. So if n is equal to 4, this entire interval has to be, 4 equal parts h shown in the diagram. So we have to find out the values of f starting at the lower bound at this point. Then we find out the f value at this point, the first intermediate point. Then we jump to this point. Then we jump to this point. Then we jump to this point. Like this, we keep on jumping and finding out the values of f, comparing till our till the f value started increasing, we stop it. H, the f value decreases, we keep on moving one after another, compare and move ahead. So if n equal parts, so we'll have here n minus 1 intermediate points. So here you see n equal to 4. So we have 3 intermediate points, 1, 2, 3. And 2 boundary points at u and v. So total how many? 3 plus 2, 5. That is n plus 1 points we need to find out the values of f. So the total search point will be n plus 1. N minus 1 intermediate point plus 2 boundary point. So it will be n plus 1. So here it is 5. So if n equal part, then width of each sub-interval, this is the total interval. We are dividing into 4 interval. So we are having 4 sub-interval. Each sub-interval, the width will be equal to how much? That is d, that is equal to total length is v minus u divided by n. So v minus u divided by n will be the width of each sub-interval. So first point, find out the f value at u. Then next point will be u plus d. Next point will be u plus 2d. Next point will be u plus 3d. Next one will be u plus 4d. Like this, we have to move. Okay, this is whatever I told you has been written down here, that we search for the minimum point at all the exhaustive number of equally spaced points. Here, of course, 5, but if you want to more accuracy, you can divide it into 1,000 equal parts. So at 1,000 plus 1, 1,001 search point, you have to find it out the F value. Quite exhaustive procedure. That's why exhaustive search method or equal interval search method. And here search begins from the lower bound U and it proceeds from lower bound to upper bound with equal step size. Look at this figure. So here this is a f of f versus x. So here f value initially decreases, then becomes minimum, that is an integer. So suppose we have chosen this initial search interval U to be like this. Then we take any 3 intermediate points in this interval UV. And at x1, x2, x3, the values of f is calculated. So let's say f of x1 is f1, f of x2 is f2, and f of x3 is f3. And then we compare these 3 values, f1, f2, f3. If x increases here, if f3 is less than f2, which is less than f1, or in other words, f1 is greater than f2, that is greater than f3, what does it mean? That means x increases from x1 to x3, f value decreases from f1 to f3. So what information we get it from here? That we should proceed further because the direction in which we are moving is a favorable one because f value is decreasing. And since our objective is to minimize, we should be happy that we are proceeding in a correct direction. We are proceeding in a direction in which f value is decreasing and we'll find out the minimum value if you proceed in the same directions. So that's why you continue the search in the same forward directions. But the moment it starts increasing, then you should stop because there is no point in further proceeding because x value will start increasing and minimum point already we have crossed. See here. So 3 points, x1, x2, x3. So f1 to f2, it is reducing, but compared to f2 to f3, it has started increasing. So f1 greater than f2, but f2 is not greater than f3 here, that is less than f3. So once you get such relationship, then you must immediately stop. And then you declare what? The minimum point lies between what? x1 to x3 or x2 to x3 here? Yes, in this particular diagram, where minimum point is lying. Look at the figure and tell me.
Between x1 and x3.
But also you can tell from this diagram, it is lying from x2 to x3, if you closely observe, right? Isn't it, in this diagram?
Yes, sir.
But this may not be true in all the cases. If this is the condition, if it is satisfied, it doesn't guarantee you that it will always lie between x2 to x3. Let us see the other diagram. Okay, the same thing, whatever I told you, that you have to compare the values at 3 different places. And if this relationship is holds good, you keep on searching. So x1, first you x1, x2, x3. And if the f value is reducing, then you proceed to x4. So this will be your next 3 consecutive values at which you should search for that relationship. So x1 you remove and then you add x4 here and you compare with x2, x3, x4. In the next case, next iteration, you compare x3, x4, x5. Like that, one by one, new point you add it and the oldest point you delete it. So at any time, there will be 3 values to be compared. Okay, so all the time, it will not be x2 to x3. Let us see. In this case, you see, although here also f1 is greater than f2. See here, f1 is greater than f2, means f2 is less than f1. But f3 has started increasing, means f3 is greater than f2. But in this case, also, although it is the same relationship, but here minimum point is not lying between x2 to x3, rather it is lying between x1 to x2. So for the same relationship, there is F1 greater than F2, but which is less than F3. That means F value has started increasing. We should stop. But minimum point, in one case, it is lying between X2 to X3. And in another case, it may lie, just like in this diagram, it may lie from X1 to X2. So that's why combining both the cases, here it is X2 to X3, the one that we have discussed earlier. For the same relationship, F1 greater than F2, less than F3. F1 greater than F2, but F2 is less than F3. But here minimum point is lying between X2 to X3. So combining both these cases, case 1 and case 2, that is, it may lie from X1 to X2, or it may lie from X2 to X3. So taking union of these two cases, we'll be getting, we can safely write down that minimum point will lie from X1 to X3. Is that clear? The one that we are pointing out, you are correct. So safely we should write down that it lies between X1 to X3. Now the algorithm, whatever we have discussed, the algorithm can be written down like this. Assume in the first step, initialize the search interval U to V. Then assume that how many equal division we have to take, that is n. So thereby in the next step, you calculate the width of subinterval, that is d is equal to v minus u by n. Then next, what do you do? Always you should consider 3 points, 3 consecutive points, x1, x2, x3. And initially the x1 will be u, because we start from the lower limit. x2 will be x1 plus d, and x3 will be x2 plus d. One step ahead. Then find out f1, that is f of x1, f2, f of f2, x2, and f3, f of x3. Now this f1, f2, f3, we have to compare. So if f1 is greater than or equal to f2, that is, but less than f3, then time has come that we have already crossed the minimum point, so we should stop. So before stopping, you write down your print command, you give a print command that minimum point belongs to the interval x1 to x3. So don't write here x1, x2 or x2, x3. You must write down x1 to x3, otherwise there will be mistake. If it is not satisfied, means what? That if f value is not started increasing, that means you have to continue the next search. We move to the next 3 points and again compare, and we have to decide whether you have to stop or you have to move ahead. So the next set of 3 points will be what? The x2, the earlier x2 will be now your first point, that is x1. And x3 will be your second point, that is x2. And now the x3 will be what? One step ahead, that is x2 plus d. Right? And whenever you write down your computer program, always you should prefer the substitution if possible, and avoid the arithmetic operations. So here I am doing 2 substitution operations, only 1 arithmetic operation. The more and more arithmetic operations if you include, that means we are asking the CPU to do more and more calculations, and the CPU time will be required to calculate will be more and more, and your program will be less efficient. The function evaluations, the number of arithmetic operations should be h lowest possible for any computer program. Okay. Now by this, like this, if you reach to the higher limit, that is the right hand side, that is the v value. So long as x3, the x3 value is less than or equal to v, you keep on doing it, the searching, go to step 3. Otherwise, you declare that I have searched the entire search space u to v, but we could not find out the minimum point. So x minimum, if x3 exceeds v, if x3 is greater than v, there is the else command, the minimum point does not lie in u to v, or it may be also possible that minimum point may lie at u or v. See this case, if you have selected uv in such a way that, if this is the way you have selected, you start from u and proceeds up to v, but nowhere you will find out that f value will start increasing. That means you will not find out any minimum value. Possible this case. Similarly, if you have selected such that u itself is at minimum point, so by that logic, that what from here onwards you start, you take 3 different points, and when you calculate, you find that it is not decreasing, it is increasing. You immediately stop and you declare that x minimum is not found out.
Sir, your voice is not audible, sir.
Author join करूँ असले okay, thank you. So is my slide visible? Hello,
No, sir, no.
slide is it visible?
No, sir, no. ଆପଣ ସେୟାର କରନ୍ତୁ sir.
अच्छा आउथरे शेयर करियो बोले.
ହଁ. ଆସିଲା sir, ଠିକ ଅଛି.
Okay, now is it visible na?
ହଁ sir, sir.
Okay.
Previous slide, sir.
Okay, so now in before that connection went out, where are we? Here. Right now,
Previous slide, sir.
Previous slides. This one?
Yes, sir, yes.
Okay.
Sir.
So what I was telling that if the UV is so selected that V is lying, sorry, X minimum is lying, V is at X minimum. So we'll search the entire the U to V, but we will not get the X minimum. So there are 3 cases. Either X minimum is at V, or X minimum is at U, or X minimum is not lying between U and V. If that you have searched the entire search space, X3 is greater than V, so you stop it there and declare that like this. Means we have not obtained entire search space from U to V, we have searched, but we did not get a point where that relationship we got it. There is F1 greater than F2 but less than F3. Means F has not yet started increasing. Okay. So that's why this out of these 3 may occur. Okay. Now let us solve this example. So this is a single variable optimization problem. Only one x is there, x, and there is no constraints. So it is unconstrained problem, and we'll be using exhaustive search method to find out this, to minimize this objective function f. So initial search space we have taken 0.1 to 5.1, and number of equal division will be dividing equally into 10 parts. Okay. So here 0.1 is u, there is lower bound. 5.1 is v, upper bound. And this 10 is small n, there is number of equal division. So next step we have to find out the width of each subinterval, that is small d, equal to v minus u divided by n. So 5 minus 1 minus 0.1 will be 5. 5 divided by 10, it will be 0.5. So thus, the step size is 0.5. So now you take the first 3 points. So x1 is equal to u, the lower limit, that is equal to 0.1. x2 will be x1 plus d. So from 0.1 plus 0.5, there is 0.6. And x3 will be x2 plus d. So x2 we have calculated 0.6. So 0.6 plus 0.5, 1.1. So at these 3 points, there is 0.1, 0.6 and 1.1. Let us find out the values of objective functions. So at 0.1, the objective function value is 0.1 square plus 16 by 0.1. There is 160.01. At 0.6, it is 27.027. At 1.1, it is 15.755. So now let us compare these 3 values. There is the function values shown in the blue color. So as x value increased from 0.1 to 1.1, f value is decreasing. So we are happy. That means the direction in which we are moving is a correct one. So let us not stop here because f value has not yet started increasing. So let us continue our search. So let us jump to our next point. So next point will be what? 1.1 plus 0.5, there is 1.6. So we'll be comparing the function value at 1.6. Just before that point is 1.1. Just before that is 0.6. That means we are discarding 0.1 and adding 1.6. So we are comparing these 3 values. So f value not rising, so we will continue. So now x1 will be equal to x2. So previous value of the x2 was 0.6. So this 0.6 will be now your first point. And 1.1, which was earlier x3, now it will be x2. And now new x3 will be what? 1.1 plus 0.5, that is 1.6. Now at 0.6, already you have calculated f value. So you will simply substitute it. That is 27.027. And then 1.1 also already you have calculated. So 15.755. Only this 1.6 is the new point. Let us calculate that. So 1.6 square plus 16 by 1.6 will be getting 12.56. So now let us compare these 3 values, these 3 f values. So now also we see that this is decreasing. F value has not yet started increasing. 27.027 is greater than 15.755 is greater than 12.56. So continue. So 2 iterations completed. So like this we have to proceed. So thus let us tabulate that 0.1, first 3 set is 0.1, 0.6, 1.1. Corresponding values are 160.010, 27.027, 15.755. So reducing. So if we take next point, there is 1.6, which is 12.56, that is still reducing. So we proceed further. Just a minute. Excuse me. Hello? हाँ मोर क्लास टे चली जाए 7:15 रे सर्व है ठीक है हाँ Okay, at 2.1, sorry for the interference. 2.1, the function value is 12.029, still less than 12.560, not yet started increasing. So take next point, you take 2.1 plus 0.5 is 2.6. At 2.6, again you find out f value, it is 12.914. For the first time, now you observe that function value has started increasing. 12.914 is greater than just the previous value, 12.029. So this F3 is greater than F2. So we stop. And now you will write down that this, where we just started increasing, that is your X3, that is 2.6. And you go backward now. So 2.1 will be X2 and 1.6 will be X1. So we can write down here the minimum point will lie between X1 to X3, that is 1.6 to 2.6. So this is the result. So thus, using exhaustive search method, we can now identify, we can reduce the interval and say that in the interval 1.6 to 2.6, the minimum point will lie. Numerical method will never give us the exact value. It will give you always an interval estimate. Means it will tell roughly that minimum point will lie anywhere between 1.6 to 2.6. And if you want to increase the accuracy of this result, we have to reduce this solution interval. If it is less and less, means our accuracy of the result of the numerical method will be more and more. So this is all about exhaustive search method. Any doubt in the logic? Now we'll see how we can do in the computer programming in the MATLAB. Yes. Any doubt till now? One by one, you just go on adding from the, you start from the U, go on adding D and find out the function values at each of this point. The moment it starts increasing, you stop and then declare that point is X3, then go 2 steps backward. So X2, X1. So we can write down minimum point will lie from X1 to X3. Yes, any doubt? Hello, am I audible?
Yes, sir. Yes, sir.
Okay. So let us now write down the. Let us check now. What is the head U? Because it is very simple functions. If you would have solved it analytically, what would have been the result? Let us check it. So f of x is x square plus 16 by x. So the first derivative will be twice x minus 16 by x square equal to 0. So when you solve it, you take 2, now multiply x square is 2x, so it is 2x cube minus 16 by x square. Now this x square into 0, this is 0. So 2x cube minus 16 is equal to 0. That means 2x cube is equal to 16, x cube is equal to 8, so x is equal to 2. So at x is equal to 2, now let us find out the higher, means only here only one optimal point. Let us check whether it is minimum or maximum. So take second order derivative. So second order derivative will be 2 plus 32 by x cube. And at x is equal to 2, if you put it, the double derivative will be 2 plus 32 by 2 to the power 3. So this will be equal to 6. So non-zero value, we stop. 6 is a positive value. So we can write down that x is equal to 2 is a minimum point. So this is exactly, you can tell that f value will be minimum at x is equal to 2. And analytically, what is that we have found out? 1.6 to 2.6. So 2 is lying between 1.6 to 2.6. So we got the correct result. Suppose we want to increase the accuracy of this numerical method, that exhaustive search method, we have to increase the number of equal divisions. So if n is equal to 5,000, finding out these solutions at 5,001 search points will be very, very time taking. Hand calculation is simply not possible. Very, very boring. So you have to write down a computer program. Okay. So this is a MATLAB program. Any line that started with percentage means it is a comment line. So this is a main file which has been stored in all the file name should have the extension m.m. So this is a main file name exhaust.m. So whatever is written here is stored in exhaust.m, and it calls for a function file, that is f.m, to calculate the values of the objective functions. So using these two .m file, we'll be able to find out the solution of this problem using MATLAB program. So these 3 lines are the input line. So u is equal to enter whatever you write down between this code, it will be displayed. Enter the value lower bound of search space u. So whatever you enter there, that will be stored in u. Similarly for v and similarly for n. So these are the three input command we have to give it. Now nf, that is a global variable. So we initialize to 0. That is to keep an account that how many times we have called the function file. Means to keep a track that how many function evaluation we have done it, we have used this global variable capital NF. Initialize the number of iterations, that is k represents the number of iterations equal to 0. So first we calculate the width of the subinterval. D is equal to v minus u divided by n. Since it is MATLAB, in MATLAB always the multiplication, division and to the power is to be preceded by a dot. It is not simply forward slash denoting the division. It must be preceded by a dot to differentiate between that whether it is a ordinary division or it is a matrix division. So if it is preceded with dot, it is a ordinary division. So v minus u divided by n, you d calculate. Then x1 is equal to u, x2 is equal to x1 plus d, x3 is equal to x2 plus d. I believe all of you are conversant with MATLAB program fundamentals. Hello.
Yes, sir. It is covered. It's a part of this course, sir.
Okay. So I need not explain in detail this one. Eh?
Yes, sir.
Okay. So I can quickly go just tell them. So in the next line, we find out, we call this f of x1, f of x2, f of x3 and stored in these three variables f1, f2 and f3. So this f is the name of that function file f.m. So here we are calling the function file f. So we are calling 3 times. So 3 function evaluation. Then we do put in a do while loop. X3 is so long as less than v. So this fprintf command is to just to add iteration wise what is the values of x1 corresponding values of f1, x2 corresponding values of f of x2, x3 and f of values of x3. So long as f1 is greater than f2 and f2 is less than f3, if it is there, then we stop and print that x minimum lies between x1 to x3. This is that line. And if you want to know in how many iterations has been shown, so number of iterations, that values of f, you can print it out. And also within how many function evaluation you got the result. So capital NF, you can print that value. If it is not satisfied, then you have to keep on doing it till that do loop is completed. And in the next in the next line, the x2 will be x1, x3 will be x2, and new x3 will be x2 plus d. And again find out f1, f2, f3, and update that k is equal to k plus 1, means one iteration is over. So this end is the for if command, and this end is for the end while command. And if you exceeds x3, v come out of that loop, and you print out this line that minimum point does not lie between this u and v, or the minimum point may be at u or that v. To print out that line, this has these lines. So all this MATLAB program has been given in that my book, that you can find out all the detail for all the algorithm. Such MATLAB coding has been provided. You can refer to that book. And this is that function file. There is function y is equal to f of x. This f must match with this f, the file name. And here you have to write down that y is equal to x square plus 16 by x. So here x dot star x, this is x square multiplication preceded by the dot, then 16 by x preceded with dot. And here nf is equal to n plus and nf plus 1 to keep a track of how many times we have called this function file. So these are the contents of the two files. One is adjust.m and then f.m. And then in the command prompt, if you simply write adjust, then the program is run. Then you enter the value u, v, and n. It will give you the result. Now let's move on to the second stage of optimizations, where we get more accurate result. More accurate means what? That whatever the interval that you have got in the first stage, there is 1.6 to 2.6, we are going to now reduce it so that accuracy will be more and more. For this, we have to use more sophisticated algorithm. Now, this algorithm based on either direct search method, which is no need to find out the derivative, where systematically we will eliminate a portion of the region where we are very much sure that x minimum will not lie in that portion. We will delete that and you reduce the interval. Or we will use a gradient based method where based on the derivative. Let us now discuss what is the region elimination method that comes under direct search method. Here these are the 4 algorithms: interval hopping, Fibonacci search, golden section search, or point estimation method. Or gradient based method, the Newton-Raphson, bisection, second, and cubic search. Okay. Now let us try to understand how this region elimination is done. So let's say this is a function, this is a minimum point, and this is u and this is v. So in this search space, we take 2 intermediate points, x1 and x2. At x1, find out the values of f of x1. So from here to here, this is f1. And at x2, f of x2 is from here to here, that is f2. Now here, f1 is more than the f2. So in which region we can say that x minimum will never lie? So if you move from the lower value, this is the lower function value, this is the higher function value. So you move from the lower value towards the higher value. And if you proceed further in this direction, you can observe that f value will keep on increasing. So f minimum, we can say that never it will lie on the left of this point. So that's why this region we can eliminate. Because minimum will never lie because f value is started increasing in these directions. So if this is the case that f1, if f1 is greater than f2, take 2 intermediate points. At 2 intermediate points, find out the values of functions. And if f1 is greater than f2, then we can say that minimum point will never lie on the left of x1. So delete left of x1. Let us say the other case. In this case, this is x1, this is x2. At x1, f1 value is less compared to f2. So let us move from lower value to higher value. So this is the lower value, this point, let us move it towards the right. And beyond this, if you still proceed, we observe that f value is increasing. But we want minimum value. So that's why there is no point in further searching beyond right of this point, where the value is maximum. So delete right of x2. So we got 2 rules. If f1 is less than f2, delete right of x2. For the previous one, that f1 is greater than f2, higher value is on the left hand side. So delete left of f1 or left of this x1. What are the other possibilities between 2 number? Either 2 number will be, one number will be more, or that one number will be less, or 2 numbers will be equal. So either f1 will be more, if f1 will be more and the higher value is on the left hand side, so delete left of x1. But if f2 is more here, if f2 is more and f2 is on the right hand side, then delete right of x2. And if both are equal, it may be possible f1 and f2, see, both are at equal height, both are equal, then you delete left of x1 and right of x2. So these are the 3 principles of region elimination by just comparing the function values at 2 intermediate points. So this is that rule. Let 2 points x1 and x2 each in the range in the interval u to v such that x1 is always on the left hand side. x1 is less than x2. If f1 is if f at x1 is larger and x1 is on the left hand side, so delete left of x1. But if f of x2 is larger and x2 is on the right hand side, so eliminate right of x2. But if both values are same, then eliminate both left and right. Left of x1, right of x2. So using these three principles, we can systematically reduce a portion of the interval, and we reduce the interval, thereby we get more and more accuracy of the solutions. Let us discuss one search method called golden section search method. So in this, what will you do? The search space UV will linearly map to 0 to 1, means we'll standardize it. And then we take two intermediate points, x1 and x2, equidistant from two end points. Two end points means u and v. So x1 will be u plus tau, and x2 will be v minus tau. From two end points, you take equidistant point. And then in this case, the eliminated region will be 1 minus tau times the space, whatever is there. And here, out of these two values, one will find out that will be common to the previous one, so that we need not have to find out the function evaluation two times, because already one is common. So thus at every iteration, we'll find out the function value only at the one point. There will be only one new point. So these values of tie is so selected that this is 0.618. That out of the 2 points, one will be common. So this 0.618 is called golden number. So that's why golden section search method. And here percentage of elimination will be 1 minus tau, that is 0.382, that is 38.2% will be eliminated at every iterations. So here the algorithm goes like this. First, initial search space U2V, that is for the variable x. And you have to define that up to what accuracies you desired your solutions. Let's say epsilon, very small value. If it is 1 decimal point, 1 decimal accuracy, epsilon will be 0.1. If 3 decimal place accuracy you desired, the epsilon value will be 0.001. Okay, first let us normalize. Let us choose a new variable z such that for the z, the lower bound will be 0, there is uz will be 0, and vz will be 1. Right? So to do that, the z should satisfy this relationship. There is z is equal to x minus u divided by the total range v minus u. So at lower limit, x is what? U. So put it here in place of x, u. So that u minus u divided by v minus u, it will be u minus u is 0. So lower limit for z will be uz, that is equal to 0. And at upper limit, x is equal to v. So numerator will be v minus u, denominator is already v minus u, so it will be 1. So thus width of space for the variable z will be vz minus uz, 1 minus 0 equal to 1. Now set iteration counter k equal to 1. Now locate two equidistant point, that is z1 is equal to lower limit uz plus 0.618 into the current width, that is wz. And Z2 will be from Vz, you take 0.618. You go backwards. Uz plus 0.618 Wz, but here to Vz minus 0.618 Wz. And at these 2 points, find out the values of functions, compare it, whichever is higher on that side, you eliminate. If Z2, if f of Z2 is higher, then you see Z2 is on the right or left of Z1. If Z2 is on the right, delete right of Z2, right? And if f of Z1 is higher, and if Z1 is on the right hand side, then you eliminate right of Z1. So you have to compare Z1 and Z2 where it is there, on the left or right. Eliminate, then update wz, and then you proceed. Then terminate till when you have reduced the width of that interval, take the absolute values of wz. If it is less than epsilon, then you stop and declare that the z value, the minimum values, that z will lie between uz to vz. That is, the corresponding x value will be ux to vx. One iteration over, k is equal to k plus 1. Go to step 2 and repeat the cycle. Let us do an example so that it will be clear to you. So here it is in the x. So for x, u is equal to 0 and v is equal to 5. And epsilon for x is 0.1. So corresponding z value will be width of interval variable. For the x, the width is how much? V minus u, that is 5. Now let us use a new variable z such that the width of this z will be 1. That is, upper limit will be 1, lower limit will be 0. We have to map it. So use this expression, z is equal to x minus u divided by v minus u. So that uz will be equal to 0, vz will be equal to 1, and wz, the width, will be 1 minus 0 equal to 1. Now, in these expressions, already u is 0 and v is 5. So let us put that u and v. So that z is equal to x minus 0 divided by 5 minus 0. So x minus 0 is x, 5 minus 0 is 5. So z is equal to x by 5 or x is equal to 5z. So this is a relationship between x and z. So this has been derived from here. There is x minus u divided by v minus u equal to z. So if z is equal to x by 5, the corresponding epsilon, the accuracy in terms of z will be epsilon x or epsilon divided by 5. So 0.1 divided by 5, 0.02. So long as the width of the z, wz, absolute value is less than 0.02, you have to keep on doing it. So that corresponding epsilon in terms of x will be 0.1. So this is epsilon in terms of z. Okay. So this is f of x in terms of x. So let us find out the corresponding objective function in terms of z. So since x is equal to 5z, wherever x, put in place of x 5z. So 5z square plus 16 by 5z. So 5z squared is 25z square and this is 16 by 5z. So this is the objective functions in terms of z. And x square plus 16 by x is in terms of x. Because z is equal to x by 5. So x is equal to 5z. So wherever x is there, put 5z. Okay, now let us do it. So let us take two intermediate points. So in terms of z, the uz is 0, vz is 1, 0, 1. Now in this uz, vz, you have to select two intermediate points, z1 and z2. So z1 is equal to lower limit is 0 plus 0.618 into, now the width is how much? 1 minus 0, so this is 1. So wz now is 1. So it is 0.618 is your z1, first intermediate point. And z2 will be what? From v, upper limit, go backwards. So 1 minus 0.618 into the width, that is 1. So 0.382. So look at here, z1 is no longer on the left hand side, it is on the right hand side of the z2. z2 is lower value, 0.382, and z1 is higher value, 0.618. So long as z axis is there. Now we have to find out what are the corresponding objective functions at z1 and z2. Let us find out f of z1. So when you put in this 25z square, in place of z, write down 0.618, 16 by 5z, z is 0.618, we get 14.726. And z2 is 0.382, so corresponding function value is 12.025. Now let us decide, we have to compare these two function value and decide which portion to be deleted. So let us look at this value. So 0 to 1 is your search space, 0 is uz, 1 is vz, and inside this we have selected two intermediate points. So z1 is 0.618, z2 is 0.382. So z2 is on the left hand side of z1. Okay. At 0.382, we have calculated the function value, and this is 12.025, which is lower than 14.726, which is f of z1. So we start from the lower value, that is 12.025, and move towards the higher value. So we are moving from left to right. And further right, if you move it, you have to delete it. Because if you further move it in this direction, f value is increasing and minimum value will never lie. So that's why here we have to delete right of this, whatever shown in the red hatchet zone is to be deleted. So delete right of the 0.618. So after deleting, the interval 0 to 1 will now reduce to 0 to 0.618. So this is the way we have to systematically delete a portion of the interval. Any doubt how the region has been eliminated? Because minimum point here will never lie on the right hand side of 0.618. Okay. This is the golden number. Okay. So then now the new, because it has been 1 0 has been now reduced to 0 to 0.618. So 0 is UZ and 0.618 will be now your new VZ. So thereby your new width will be 0.618 minus 0, that is 0.618. And absolute values of this is not less than the epsilon z, that is 0.02. So that's why we have to continue our search. And k is equal to k plus 1. First iteration is over. And then we have to do the next iterations. So like this, you have to do it iteration after iterations till this wz is less than 0.02. So this is the way iteration after iterations will get the result. And finally, we will write down here that, see here, in this case, the wz is less than 0.02. So here we stop it and write down that minimum point lies between 0.395 to 0.408. But this is in terms of z. So the corresponding x value will be x equal to 5z. So multiply 5 with 5 into 0.395 will be 1.976. 5 into 0.408, 2.041. So minimum point in terms of x will lie between 1.976 to 2.041. And this we have obtained after 9th iteration. See here, 9th iteration. First, second, third, fourth, fifth, 9th iterations. And how many function evaluations? How many times we have find out the f of x? Let us see. So in the first iterations, uz was 0, vz was 1. And the two intermediate points were 0.618 and 0.382. And at z1, at 0.618, f of z1 is 14.726, and 0.382, that is z2, f value was 12.025. And this 12.025 is less than 14.726. So we have to move from z2 to z1. So z2 is 0.382 to 0.618. So 0.382 is on the left hand side. So we are moving from left to right. So that's why you have to remove right of 0.618. So that's why 0.618 has become VZ, new VZ. See here in the next iterations. But UZ is 0. So when it is 0 to 618, the corresponding WZ is 0.618. And again we have found out next 2 points. So it is 0.382, 0.326. And you see here, this 0.382 is same as this 0.382 in the previous iteration. So we simply substitute the values of function value, whatever we have calculated in the previous iteration, for 0.382. And the new, only we have to find out the function values for 0.236. So only one function evaluation is done in the second iteration. Let us see in the third iterations. If you compare second and third, you see again 0.382 is common. And new point is only 0.472. So only one function evaluation. Again you compare between third and fourth, again 0.382 is common. Between fourth and fifth, again 0.382 is common. Between 5 and 6, 0.416 is common. So that's why at every iterations, we are doing only one function evaluation, not two. So that is the advantage why we have taken the two intermediate points at tau. U plus tau, uz plus tau z, tau, and then vz minus tau. Tau is 0.618 times the current width of the z. So only in the first iterations, both are new points. So there are only two function evaluation, whereas in all other cases, it will be only one. So that's why number of function evaluation will be one more than the number of iteration. So if number of iterations k is equal to 9, number of function evaluation will be 10. Yes, any doubt? So this is the way we find out the solutions for the single variable unconstant problem using golden section method. And here you see the accuracy is much better compared to the exhaustive search method. And here, if you compare the WZ, 1, then reduce to 0.618, then reduce to 0.382, then 0.236, like that it keep on reducing, right? So WZ is actually, you are multiplying 0.618 each time. So 1 is 0.618 to the power 0, 0.618 is 0.618 to the power 1, 0.382 is 0.618 to the power 2, 0.236 is 0.31. That means the interval after third iterations, we are getting 0.3826, means initial interval was 1, so 1 into 0.618 to the power 3. So that way you can, so we can, in other words, you can write down that number of iterations, that is epsilon. Finally, we will stop at epsilon. The interval should be reduced to epsilon. So initial interval is v minus u into, after first iteration, it will be into 0.618. After second iteration, again multiply one more time, 0.618, that is to the power 2. So let's say after kth iterations, it has been reduced, v minus u has been reduced to epsilon. Then you can say that k iterations is required to obtain the solutions to an accuracy of epsilon. So this is the expressions to find out the number of iterations required to get the desired accuracy epsilon. And in terms of number of function evaluations, instead of k, you can write down n minus 1. If the number of evaluation is 1 more than the k. So at each time, interval reduced to 0.618. That is 61.8%. That means we are eliminating 100 minus 61.8, that is 38.2%. The region is eliminated. So same problem, if you want to find out an accuracy of 0.001, manually not possible, you have to write down a computer program. And use that MATLAB program. Similarly, you can write down your own MATLAB program or refer to the coding that is given in my book, and you run it, you will get that the minimum point will lie between 0.4 to 0.4, or a corresponding x value will be 1.999 to 2.000. That is within 18 iterations, you will get it. That is after 19 function evaluations. Now coming to gradient based method, here you have to take the help of the first derivative, right? Because at optimum point, first derivative is 0. That means the tangent at that point is a horizontal point. So if you get the first derivative 0 or approximately 0, we stop it. So Newton-Raphson method, here we start from an arbitrary point, then we move from one point to another point. It is not like that interval, we are reducing the interval. Here we move from point to point. So the next point is defined like this: xk plus 1 is equal to current point xk minus the ratio of two derivatives. The first derivative is at numerator, second derivative is at the denominator, and that at the current point. And then again we find out the first derivative at the next point, and if that first derivative at the next point is approximately equal to 0, then we stop it and declare that xk plus 1 is your optimal point or the minimum point. If any function, first derivative, second derivative, we are not able to find it out, we can still use the Taylor series expansions to find out the approximate values of derivatives. So your algorithm goes like this: initial point x1, then we specify the maximum permissible error epsilon, very small value, iteration counter k is equal to 1, calculate first derivative, calculate second derivative at the current point xk. Next point, use these expressions to find out next point. At this next point, find out the new gradient, the first derivative, and check that absolute values of this new, that the first derivative at the new point, is it less than the desired accuracies, the maximum permissible error epsilon? If yes, stop and declare that this new point xk plus 1 is the minimum point. Otherwise, k is equal to k plus 1 and you repeat the cycle. Let us solve it. The same example starting from 0.1 using the Newton-Raphson method, and let us first solve it using exact differential. Means difference taking the exact derivative. So f of x is x square plus 16 by x. First derivative will be 2x minus 16 by x square. Second derivative will be, for 2x it is 2, and minus 16x square will be 32 by x cube. So iteration counter k is equal to 1, x1 is 1. So at x1 is equal to 1, find out first derivative. So put that x is equal to 1 here. So 2x minus 16 by x square. So x put 1. So 2 into 1 minus 16 by 1 square minus 14. At x1 is equal to 1, the second derivative will be 34. So let us substitute here to find out the next point. So k is equal to 1. So k plus 1 is x2 is equal to xk is x1. x1 is 1. And first derivative at 1 is minus 14. Second derivative is 34. So on simplifying this, we'll get 1.412. We have to check now whether this 1.412, we are getting the first derivative approximately equal to 0. So let us find out first derivative at 1.412. So at 1.412, the first derivative comes out to minus 5.20t. Its absolute value is not less than 0.1, our desired accuracy. So we should not stop here. We repeat the cycle. So k is equal to k plus 1. So k is equal to 2, and you continue. So like this, one iteration is completed. So like this, we can solve iteration after iterations, and it goes like this. So first xk was 1, then 1.412. So their first derivative is minus 5.204, not less than, absolute value not less than 0.1. So we cannot stop. So again proceed, next point 1.801, corresponding first derivative will be minus 1.331, absolute value is not less than 0.001. Again continue, 1.979, first derivative 0.128, not less than 0.1. Then next point 2.000, here we are getting first derivative 0.001, which is less than 1, absolute value less than 1. So we stop it and we declare that x is equal to 2 is the minimum point. And these are the corresponding second derivative, and this is the next point. Next point becomes the current point in the next iterations. 1.412 becomes the current point xk in the second iterations. Now this is using exact differential, but we can still use it using approximate the Taylor series, this one, by central difference method. We can find out the first derivative and second derivative, for which this is the expressions. We take 2 points at x plus delta x and x minus delta x, find out the f value, take the difference, divided by the total difference is twice delta x. So this gives us an approximate values of rate of change of f with respect to x. So this is first derivative. And second derivative will be f at x plus delta x minus 2fx plus f at x minus delta x divided by delta x square to find out the second derivative. Now this delta x value should be equal to 1% of the current values of x, absolute values of x. But if x value itself is less than 0.01, then we take delta x value 0.01. So this is what should be the values of delta x? That depends upon the value of current x, the current point, and these two relationships to find out the approximate values of first and second derivative. So you can use the same example using the approximate differential. So here values of x each 1. So its absolute values is 1. Multiply 0.01. So since it is more than x1 values is more than 0.01, the delta x will be 0.01 into absolute values of x1. There is 0.01 into absolute values of 1, so that is 0.01. So thus x1 plus delta x1 will be 1.01, x1 minus delta x1 will be 0.99. At these two values, 2 points, we have to find out f at x1 plus delta x1 will be 16.8x1684, and x1 at x1 minus delta x1, that is 0.999. Corresponding f value is 17.14174, and this is the f of x1, that is f at 1, 17. Using these three values, we can find out the second derivative, and using these two values, there is x1 plus delta x1 and x1 delta x1, you can find out the values of first derivative. Let us find out. So first derivative at x1 will be, substituting those values, we will be getting minus 14.002. See here, approximately equal to minus 14. Exact values will be minus 14, but this is minus 14.002. And second derivative will be 34.003 instead of 34. So thereby x2 will be 1.412. And then remaining procedure remains same. Only here is that we are finding out the derivative using approximate method. Same, otherwise procedure is same. So same, here also we will get x minimum point is equal to 2.000. So thus we have learned in today's class how to find out the optimal solutions for a single variable unconstrained optimization problem. First we learn analytical method, taking the derivative, first derivative and then higher order derivative, and finding out the local maximum, local minimum or point of inflection. Then we learn the three methods. First is exhaustive search method to find out the initial bracket, and then one method we learned, there is golden section method from the region elimination group of method, and one that Newton-Raphson method from gradient based method to find out the final solutions depending upon the desired accuracies. So to find out those MATLAB program, either you can write down your own code, or in MATLAB there is an optimization toolbox. So there this 1, 2, 3, 4, no, this this f mean b and d, to find out for the single variable, you can find out the solutions for this a single variable optimization problem. For multivariable, these are the other subroutine in optimization toolbox. And for constraint problem, fmin com can be utilized. So for the single variable, using the MATLAB optimization toolbox, we can still find out the solutions directly. So let us solve this same problem using MATLAB toolbox. So we have to use f mean b and d. This is a single variable unconstrained minimization problem. So either you can write down this on the command from this command, where you write down this f mean b and d, and here you specify the objective function, there is x square plus 16 by x, then comma, the lower bound is 0 and upper bound is 5, u and v. Or you can, from the menu box, you can choose this apps. First you click on the top menu, then you click optimizations, or from the command prompt, if you write optim tool, you can invoke this optimization toolbox. Apps you click, then you click optimizations, so that you will get a box like this in optimization toolbox. And here you select the solver, Here you select in this that drop down menu. If you click, there will be many subroutines will come out. In that you select admin BND. Even if you forgot this exact name of the subroutine, here the detailed name will be written here. Single variable non-linear minimization with bounds. We are providing the boundary U and B, and it is a non-linear minimization problem, and it is single variable. In that, in objective functions, you write down @f, means at f.m file, it will search for m.f file to look for the objective functions. And lower bound x1, you put 0, and upper bound x2, 5. Then you put start, it will give you the result. Admin BND, objective function @f means function file name is f.m, x1 0, x2 0, start, you put start, you get the result. The final point is 2 within 8 iterations. So with this, we complete the single variable unconstrained optimization problem. Either you can write your own MATLAB code or use this MATLAB optimization toolbox, and you can solve an unconstrained optimization problem. Any doubt? If it is there, please ask me. Otherwise, we conclude with this.
No,